Okay, we are live for day 25 of Additive Code, and early because we still have not finished day 24, part 2. And I have two ideas for how we can approach this. So I think I'll try them both out. The second idea, this will be my backup, is to solve directly a system of equations. We only need three of these. In fact, if I have to, I might just take 3 hailstones, solve them by hand, find a line that will intersect through all 3 of them at appropriate times. And if I need to, like maybe with just 3 lines, I can do like a guess and check over those, which is not a bad idea. But I want to avoid things that are risky because I'm running out of time. But the first idea I want to do is continue what I was doing yesterday when I left off, which is to start with a guess. Start with a guess for direction and precision, and then use the data about how far off the time deltas are to improve our guess. So how much did we miss? Can we consistently take a guess and turn it into a better guess? And if so, we just iterate on that repeatedly until we have the best guess, or close enough, whatever. We're working with doubles as soon as it's not the delta between guesses is not moving that much, then we should be good. But to do that, we have to explore this problem space first. And you know what? I have a visualization or an idea for how to visualize this. So let's draw more charts. We're going to go into new territory here. Okay, so looking at just one dimension independently. So let's say, oh, this is annoying. Okay, I have to, Microsoft Whiteboard. I don't recommend it. I'm going to find a better whiteboard. But I don't know. It shouldn't be synced. It shouldn't be synced online. You shouldn't have to log in or anything. It's not the most intuitive to use. You know what? Just give it a space. Yeah, this works. We're gonna look here. Okay, so this is how I want to visualize this. So think about just one dimension. So here we'll have x. And then on the other dimension, I'll plot time. So here's x, and here's time. And we have a bunch of different starting points for all of these hailstones. They all start at 0, but they have different x values. So we can plot them this way. And then they all have different velocity vectors in the x direction. So some of them, the x is decreasing, and it will look like that, right? And then some of them, the x is increasing. And I did verify they do alternate somewhat. So like you can have something go in that way and then out that way and then back in that way, right? So there are all of these going in some direction there. I don't know about the very outer edges, but what that tells me is if you want to throw a stone that eventually intersected with all of these, so let's say we throw a stone from, I'm going to extend this graph down further. If we were to throw a stone from all the way down here, in fact, let's say this thing is now my stone. Then let's say it intersects a bunch of things. Well, let's just draw a bunch of blocks or whatever. If we throw it from down here, in order to intersect with all of these, let's say one of these is moving up positive x, it needs to catch up with that eventually, right? So the most positive x, our guess has to have a faster speed than that. So this in that direction won't work because it'll miss a lot of things. But if we go at more of an angle, that is to say higher velocity, then it'll eventually intersect all of them. And that's a potential answer, at least just in the x direction. That tells me that in the x direction, we could have a high negative velocity or a high positive velocity. There. What else do we have? We have, it, if it has a high positive velocity, then it's probably not going to be here somewhere in the middle because we do have to intersect with all of these. Not all of these might like cross over this way if we were to go out in this direction. So I don't think our x value is going to be starting from somewhere in the middle of all the other x's. It's probably going to start off to one side or the other. And that's, again, just because there are cases like this where this is positive, this is negative. We can't possibly catch up to both of those, right? Okay, so that makes sense. We'll move on here. Um, and yeah, well, let's move this over to the right. And let's start looking at some data. So again, you have to have a high negative or positive velocity for this to even work. And if we're looking at time deltas, then the time of intersect for all of these needs to be positive, right? You can't be intersecting back here in a negative time. Okay, so let's look at some of this data. Where did we have? I just want to look at the values right now for the x velocity, the min and max of those, and the min and max. I think I had them like a sort by in a print line somewhere. Sort by here. Okay, so this here has velocity. And here's an example. Well, okay, these are all negative velocity, and they're all pretty high. All of these are E14, so they're all like this long. I wonder if I just divided them so they're easier to read. Like I divide by whatever this value is, with a 1 on top of it. Okay, let's try that. Velocity to position divided by foo. Okay, a little bit more legible. We see our like mins and max positions. So these here at 2000 seem to be close to our min position. In fact, let's get our min and max velocity. So hailstones dot map. Let's just get h dot position dot x and min. Let's look at min and max. And we'll also look at velocity. Oh, this h can be an underscore. Okay. And then velocity dot x. Okay, so our min x position is like 1.3. Our max is 5.5. So as we're looking at this, we see here this is a negative one, a one with negative velocity, the high negative velocity. That, I mean, I guess they're not that low. I don't like the dividing by foo idea. It's fine, just read at the point. Yeah, there's a mix. There are some 4s in the positive, and in the very positive x velocity, they tend to be lower. All right, so they all tend to be like going inside, but there are exceptions to the rule, and we can see that more clearly when we look at them sorted by the position. I think I want to truncate the position so it's easier to read. So x dot position, x dot truncate. Is there a round, round, divide by foo. Let's do that. I just want a shorter number. Okay, this works. This works. Um, so this is from the bottom to the top. I think I want it from the top to bottom. Okay, so all these top values do have um, negative directions. So when do we first get a positive direction? Well, actually, at a pretty high value, 4,000. That goes up 22. So that is on our graph as if we had, a bunch going down. And then this one here, we get like a positive. It's not very positive. It's like positive 22, but it's not pointing down, is it? And so we probably have something similar on the bottom. Um, and then we have tamer values towards the center and more extreme values towards the outside, with some crisscross, whatever. And so generally forms like this kind of a shape. And we have to throw a rock like down here that goes all the way through there. And it's probably down pretty far, to be honest, if we want them all to be positive. So let's test some values to figure out like where a good starting point might be. Um, Now here we're counting x's that are positive. We have a pretty high positive velocity. It doesn't seem like, well, the velocity does matter somewhat. Let's take our highest one. Um, yeah, let's take our highest one and let's make it higher. Because you need to be able to catch up with everything that's ahead of you. Now this tells me like there might be stuff behind me that I'm missing. You're starting at max bound times 0.5. So we're starting at the lower bound, and I think we need to start much lower than the lower bound. So let's try position. Let's just say x starts at 0, which is well below that lower bound. Here we have 139. Again, just changing the velocity much. Right, the time deltas will be more extreme, but we still do get the same number of these intersects. Wow. Let's try like negative max bound. 139. 139 is the best we get when we have a really low bound. Okay, let's try the other direction. So I'm just gonna, yeah, let's try positive max bound, and we'll multiply that by 2. And this is, wait. This is negative max bound with a positive velocity. So I think we decided that if we have a positive max bound, if we're starting near the top, we want to have a negative velocity, don't we? Otherwise, we're never going to catch up with any of them. If this goes up too high, let's say, times 2, this should go down really low. And interestingly, that is not down all that low yet. And max bound is pretty large. Let's just multiply it by 8, see what happens here. Like eventually we want to get all these to be positive, right? They all do have to be positive at some point. Um, let's see if we have a really high starting value and then we decrease it a lot. We also get 161. That's interesting. Um, that tell me that there's stuff we're not able to catch up with. So let's say zooming I don't know. Let's give this another go here. And we're zooming out a bit. So now all of our values are like here and here, right? So if we start really high and have a really negative velocity, then we should be able to intersect them all. So the delta for all of those should be positive. Um, and I can check how I'm computing that delta, or not the delta, the time value, the t value for the intersect. um, so if you start really high, and we have like a really big negative velocity, we should hit all of them. And deltas, we have a rock guess. And each of these, so we're solving for time. What does that look like? So you have a hailstone. Hailstone has an x position. So our hailstone has an x position and an x velocity. So position equals velocity times time. And then we have the same for the rock. So if we set time equal, so P over V of our hailstone should equal P of rock over V of rock. Wait, is that right? Yeah, okay, I think our formula that's in VS Code might be wrong. Um, so what do we want to solve for? Let's say we're solving for just the x position. Wait, I mean these two things are constant. Oh, you know what we want to solve for is actually time. So given all these are all constants, and given all of these constants, how do you solve for time? So time. Oh, hold on. There's more to this. Um, so this is position at 0. What we have is constant is position at 0. So let's rewrite this. Position at a given time equals position at 0 plus velocity times time. And what we have here is that PT for the rock should match PT for the hailstone. So PT whatever. So this is a position of, let's say this is the hailstone up here, and this is the rock. The position 0 of the rock plus velocity of rock times time, which is what we're solving for. So we have position at 0 for the hailstone, pH plus its own VT equals P rock plus its VT, and to solve for time, we're going to do, let's move everything to the left. So velocity of hailstone times time minus velocity of rock times time equals position of rock, the x values of the rocks, by the way, minus position of the hailstone. And we take time out of the equation and move it over. So we have t equals, we factored that out, Position of rock minus position of hailstone over velocity of hailstone, right? Minus velocity of rock. No, yes, velocity of the hailstone minus velocity of rock. The way we formulated that might actually be two different ways: a positive time and a negative time. Well, actually, I'm not sure. But that looks distinctly not like whatever's going on here. Um, so let's comment that out. So what we should have is PR minus pH. So we'll say rock guess dot position dot x minus x divided by um, hail position or hail velocity. So the hailstone velocity minus rock guess dot velocity dot x. Okay, and so now that's just for the x's. And this looks more like we were expecting. Maybe. Yeah, actually, in some of these cases, we get 300s. So this is good. This is good. Let's get Copilot to autocomplete those changes for the others. Okay. And let's just delete most of them. So this velocity 1000. Okay, so this is a low position. Let's try something higher than that, or even lower than that. So let's say minus max bound. And then a big positive velocity. Oh, 0, 0. There we go. Let's try a bigger positive velocity. Whoops. Yeah, it doesn't like that typecasting. Oh, interesting. I mean, let's try max bound. Starting at a high position with a high x velocity. That seems backwards. And we need to start higher than max bound. Set at times 2. Yeah, that would catch all of them. Interesting that they are both positive. There might be a slight mistake here, because that shouldn't be the case. So the setting position after time equal. So we have this offset pH, VHT, whatever. The hailstones are on the left. In fact, what we're doing, let's just formulate this in the other direction. So position of rock minus velocity or plus velocity of rock times time equals position of hailstone plus velocity of hailstone times time. And we move, let's move this all to the left. So we have VRT minus v v ht. Whoops. V ht equals whatever, and t is going to equal that whatever and be pH minus PR over, when we factor this out, we have VR minus VH. Yeah, and that's the same thing, but negative. I like that ordering better. So pH minus PR. This is a hailstone. How do we write this? Let's say X minus that. And then VR. Oh wait, precision of hailstone minus, and then VR. So the rock gas minus XV. Okay, and we'll copy those. And this might be more what I was expecting. No, it's actually the same thing. Um, but you know what? Let's see. At some point here, velocity should start mattering. So if it's 100, it's not going to catch them all. If it's 1,000, it's going to be able to catch them all. It should be able to catch them all because it's faster than the fastest rock going south. In fact, like 500 should be enough. And let's say, given that it's 500, what is kind of our, let's say max bound times 1.5. That still hit 300. Okay, and then from the other end, we should be able to do something. So let's say we start from 0, position 0, 0, 0, and velocity is negative 500. So that is a potential. So what we could do is try all of these variations of negative 500, 500, whatever, and see which gives us the smallest deltas. Or these aren't deltas exactly, these are the times. Let's rename that times. And then we can compute deltas. We could do like a standard deviation of all the x's. We could compute like the average and see how far away each is from the average, because like we want all of these to be the same, right? We want this to be to average to 0. I mean, they would average to 0. We want them to be the same, right? Let's check min and max values for y and z as well. So where had we been doing that? Dot max. Here we go. Let's do that for y and z. Okay, interesting, interesting. Oh, this is the min position. It's much smaller. That's E12 instead of 14. And yeah, so we go from like 2 to the whatever, to whatever power of 10 that is. 2 to 4. So we can go from basically from like 0 to 6. And I think that should be far enough out. So let's see, valid starting positions. I guess each gets paired with like bound. So let's do a 4 comprehension. Hmm. Um, I guess we have bx, or let's just do like the x values. These are gonna be paired. So let's have like this coming from whatever this is. It's coming from a list of 2 values as negative 500, um, which gets paired with 0. Let's just do position velocity. So 0 to negative 500, and then 3 times min bound to positive 500. And let's say this is x and xv. And we do that for y and z. And let's just autocomplete for z. And then we yield a hailstone. Well, start candidates. So these are going to be candidates for a starting guess. We're going to take the one of these that has the least deltas, or like the least differences. So start candidates dot map map times. I guess we could do this for each print line just to see that they're all like 300s. No, this is just the x value. Oh, and this is an int or long. We are expecting a double, right? Let's just do 0.0. Okay, so we're gonna do a count in the case here. Just so case xt yt zt xt equals 0 and yt equals 0 and zt equals 0. I was hoping Copilot thought complete that. And zt equals 0. Wait. No, that should be 300. And then that should be all of them. Okay. Great. And oh no, that's actually not going to be the case. You want like a for all. Or you know what? It doesn't matter if we know it works. what we want actually want measure these. So given a bunch of times, um, we want the distance of each of these from the average. Def. Let's do like the standard deviations. Variance, whatever. Call it dev, and we have times, which is gonna be the same type list of double, 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 and we'll do times dot map case. And now we can take those 3 times. Val a equals average divided by 3. And then we want the difference of each of those from average. So xt, oh, yes, that works. This is the standard deviation. Each row, I guess the standard deviation for each from its, we don't really need the standard deviation, right? We just want the total variance. Um, so xt minus a, and then we'll get like dot abs, and then we do that for the other two. Yeah, that's just like the total distance. And I guess where the total distance is the closest to 0. Yeah. So we take the star candidates, we map times, and we map dev. And then I guess we could take the dev of that, and then we could sum. And we'll do a for each print line. And one of those is going to be a better candidate than the others. Maybe like all of those should be candidates for improving. There are a couple that look better. Actually, they're roughly interesting that half of them are about 5, and the other half are about, I wonder why that happens. And we have an hour left. So continuing to focus on that. How do we improve this? So one thing we could do is we could take times. How do we improve a bunch of guesses? So let's go to one of these graphs. Let's go to this one here. So like say the x times are generally higher than the y times. So one way we can decrease the x times is by moving x closer, right? Like if they are all higher than the y times, or if they are all like higher than the averages. Yeah, what we might want to compute, instead of what we've done there with like summing all the averages, we might want to keep them separate. But if they are generally all higher, then we just shift x a little bit in the appropriate direction to make that lower, right? So let's do another thing here. And instead of summing those, we will tuple them. and we won't take the absolute value. We are subtracting the average from each, which is to say, like, if xt had a time of 3 and the average is 5, then if this is -2, then that means it needs to go down. Xt needs to go up by 2, right? Okay, I'm curious what that looks like. So we're gonna map times, map dev2. Oh, right, it's gonna do this for each of these. And then I guess we can map some on each of those rows. We can get 3 lists. Let's do like a dev2, and then let's do some unzips. Yeah, unzip 3. Cool. The x's, y's, and z's, and we can just sum those. X's dot sum, y's dot sum, and z's dot sum. Okay. So in this example, we can stand to shift x by however many whatever. And we could use these to find, I don't know that there's like a best starting candidate here. We'll just take the head one, and we can experiment with that. So val c equals start candidates dot head. And let's experiment on what it looks like to improve that. So times of head of c, and then dev2. And if we modify c somewhat, so looking at that x value, for example, it is generally pretty far behind on time. So if we increased the x value that started with, let's print c. What is c? Okay, position 0. Right. So if we increase the x value, actually we only want to change, yeah, we want to change the c position, c dot position dot copy, and x equals c dot position dot x. Let's just do half of the min bound plus min bound divided by 2. Enough friends there. And that made the times much worse. And in fact, let me just check if still needs to hold that we still need the x values to all be positive, or the x times. I'm starting to anticipate that this might be slower than solving directly with a system of three equations. Um, and we can do that with hard numbers even. Uh, yeah, we solve for like T1, T2, T3, and use that to solve the rock decision. Um, hmm, but let's see. What if we did C dot or no, we want min bound. Min bound divided by 2. I guess this has to be a negative velocity. I don't know why. Seems like that's opposite what it should be. Um, it does not appear to be running, updating. Okay, let's let that rest in the burner. Let's just think about doing it the other way. We'll just take 3 values from day 24.text. And we can call them hailstones A, B, and C. um, well, no, let's just get them sort of randomly from the middle-ish. Here, we'll call this A. Or H1. Did I define H1 elsewhere? Yeah, I kind of did. We'll call them S's now. S1 equals hailstone dot parse S2 equals hailstone dot parse. Don't give me fake values. Okay, let's just get another one somewhere in here. Sure. Oops. And then another one somewhere in here. S3 equals. I wonder if I'll know to use that. Whatever. Oh, interesting. This has too much stuff. Um, those 2 lines are identical. I miscopied somewhere. Okay, again, with this, let's just go right in here. And that is what the 3 equations that we'll use to solve for T1, T2, and T3, which should help us get the position. So we could solve for T1. There's our walk. So again, we had the general equation. Position of rock. We'll use subscripts. So for the numbers. So position at rock at T1 intersected one of those equals just the starting position of the rock plus the velocity times time. The velocity of the rock times time 1. right? And then we have stuff like P1 should also equal the position of rock 1, or position of hailstone 1, um, the start position of hailstone 1, but pH1 plus velocity of hailstone 1. So we could say V1 I'm going to call this PR1. And this is the starting position of the hailstone. So I guess we can just call this P1. We'll figure that out. The position of hailstone plus velocity of hailstone 1 times time 1. And this whole thing is going to be P1, which honestly we don't even really care that much about. And we have 3 equations like this. So I'll copy paste this. And you know what? Let me just switch up some of my audio here. Okay. I'm gonna copy paste this. We are running low on time. I think if we're committing to this, this is actually how we're gonna have to solve it today. So we duplicate that, move around, we're gonna change this to 2s, copy, paste again, and we're gonna change this to 3s. And I think that should be enough because what are the unknowns we're trying to get? And let me change some of these. We're trying to solve PR, basically. And of course, these P's and V's being like 3-dimensional. So this is 3, 3, 3. The V's are constants. I could mark in color what's constant and what's not. So here's a 3, 3, 3. This is the position of H. Yes, it is, but it's the starting position of H1. So these are going to be 1, 2, and 3 as well. 1, 2, 3. And the things that are variables are going to be here in green. Oh, yeah, let's just make that complete. 2, 2, 2. And we're going to copy that whole thing so that we can highlight stuff. Okay. What happened to my pen choices? Here we go. Okay, so T1 is a variable self for T2, T3, since we have 3 equations, constant, constant, and then PR and VR are things to solve for. So therefore, 3 equations, there are 4 variables. We might need another equation then. So can we relate? If we tried to solve for PR and then start substituting things in, what do we get? So let's start with the first line. So PR equals, um, so this is constant. There's that variable. We want to take those out eventually. How do we relate? How do you relate that to these here, though? I suppose we could solve for VR and then replace them there. Yeah, we could solve for VR and then do a substitution to take VR out of the equation. But then we still have the different times, right? How do we relate times of these to each other? So PR equals P1 plus V1 T1 over VR T1. I guess we could relate two of these equations together to make it possible to get the T out or the V1 out. Yeah, one, I guess all of these are variables as well. So all in all, one, two, three, four, wait, one, two, three, four, five. We have five free variables. And I don't see how we get T1 out of these because how do we relate? I mean, no, I guess it suffices to solve for like what T1 might be for T2 to be happy as well. Um, okay, let's copy this. We'll match the PRs. So copy. Um, and then we'll write a similar equation for P2 on the other side. So 2 plus V2, V2 over VR T2. And now we could try solving for VR. I guess we get a function for VR. We get some sort of relationship between T1 and T2 that's given by, that would give you a VR. And then you could plug that in to this third equation. So yeah. Yes, that we can do. That we can do. We can just keep plugging them in. So we multiply, and what do we get? Multiply, multiply. I guess we just flip both of these sides, and we take out the VR. VR T2 times whatever equals VR T1 times whatever. And we can subtract to get them both on the same side. And that'd be, like we said, that equals to 0. and then we could pull out VR. So VR times something. So it'd be like T2, you still have the whatever stuff, minus T1 and the whatever stuff equals 0. And then wait, we divide both sides by that? That doesn't make sense. My algebra has failed somewhere. I'm doing something invalid. VR times this should equal 0. Yeah. Failure. Um, I broke a rule while solving for VR, and I'm not sure which. I mean, I guess we get this relationship. We can subtract that, and we have that T2, given that they have to share the same VR and PR, we have that T2 times P1 plus V1 T1 has to equal T1 times P2 plus V2 T2. And I suppose we could do a similar thing between like T2 and T3, solve for T1. And now when you solve for like T1, T2, and T3, we can solve for P and R, right? So if we just plug in more and more equations, okay, so let's like solve this for T2. Well, except okay, let's gather all the T2 factors. So there's gonna be a T2P1. Let's group them by how many like T whatever else's they have. So there's a T1, T2, and there's gonna be T1, T2 here. So we multiply them both. I'm starting to get very diagonal. So I'm just gonna like reorient here. So we have B1, T2, T1, and the other factor. So we have a minus that's coming from the other side, minus V2, T1, T2. And then we have a plus E2. Oops. I'm not sure I like this. E2. E1. And we have a minus T1, E2 equals 0. And if we choose just to solve for like one of these T things, you know, T1. Yeah, let's just solve for T1. So T1 in terms of T2, let me see, we got moves over to this other side. T1, so this T2 gets moved over to the other side. we just have P2 P1 over. Now, when we're pulling this out, we have V1 T2 V1. Oh, I don't know why I insist on going diagonal. uh, so V1 T2 minus, we pull T1 out, V2 T2, and we're pulling T1 out, plus P2. And I guess we could get a value for T2 by plugging it with T3. How does this work? So given a time for T2, we can solve for five equations. We need, wait, five variables. We need five equations in order to solve this, right? Let's say we replace T2 here with a value that we got for T3. Or let's say we do something else in terms of like some other value. What would be T1 in terms of for P3? That doesn't help us, does it? I think that was a bad rabbit hole. Okay, so right now, do I salvage? Not really salvage, it hasn't failed yet. Do I continue working on the starter guess and improve that guess by moving things around? I think we do. Okay, where had I tried that out? So this one here, we saw our times by increasing, by moving x closer to all the points, we saw a greater difference. So here, they were pretty close. I mean, not pretty close, but closer than other things. And here, now, x deltas became very late. I think we need to move x when x is negative. We need to move it in the opposite direction to make it positive. So instead of that, let's do c dot position dot x minus min bounds over 2. This is moving it farther away instead of closer. And let's see what value we get there. This shouldn't take that long to run. It says analyze in 2 seconds. I'm just not seeing my new worksheet highlights. Man, worksheets bugging out on me has been a real pain this season. Right? That's calculated. Just calculated that. Wait, out of memory Java heap space? What other files do I have open that would cause that? 23 being here could be a pain, I guess. What else is open? Okay, let's reopen. Okay, we're seeing what direction we have to shift. Now there's also another thing that can happen here. Where is it? So it could be that the times up here differ more greatly than the times down here, right? And in that case, we could change the trajectory of the line of this x timeline. So it's like choosing between this dotted line or this dotted line by adjusting the speed. So I guess if we find that the standard deviation is too high, we want to have a tighter standard deviation of errors, right? In fact, when this is perfect, that standard deviation will be 0. Um, and we have the general distance, and we can use that to shift x and y. Okay, waiting for first run here. The first run's always slowest while it's warming up. I mean, we have 3 lines, and we can find a line. Like, if we ignored time altogether, or if we just looked for a line that intersected those 3 lines, right? Maybe I should not have time in my equation, and we should figure out time later on, the intersect times. Then we just have like 3 line equations, and we don't have these 3 time variables that we're trying to solve too. Right? Oh, let me think about that. Yes, that'll be so much easier to solve. And then it would only take P1, P2, and P3. So given this, let's go down another route. And we just want the equation for the line. I mean, if this were just like x and y, we'd write it in terms of like y equals whatever. We have a y-intercept, and then we have some factor times x. So mx plus b usually. And in this case, how do we calculate? So what does this look like in 3 dimensions? I mean, we could start in 2 dimensions and repeat the process. Um, I guess we could do like z. Let me look at this. Function y 3 dimensions. I can't afford to like be rewriting stuff. And we can just use the velocity and positions to determine those lines. And if we find a line that intersects all 3 of those lines at different points, then those points are the 3 different times. But they all provide restrictions, right? You have 2 lines in space. There are many lines that can go through both of them, but once you add like the 3rd line, then there aren't many lines that yet finds like some intersection point between these 2. Yeah, there's only 1 line that can go through all 3 of those lines. So let's do that. That's what we should be doing. I made a similar mistake last night considering time. Part 1. Okay. Hold on. Equation of a line in three dimensions. A, R, sure. Okay, so we have like our unit vectors, I guess. By Z and direction cosines. I don't want to work with angles though. I guess functions with three variables usually define a plane. This is our Cartesian equation of a line. Um, a vector form, parametric form. Okay, yes, I guess they all rely on TA. T is a parameter describing a particular point on the line. Yes. But we want to avoid okay, yeah, any line on the point, right? Um, yeah. But they will all share that T and symmetric form of it here. Mhm. Okay, so we get each of these timelines, and we sub in the T's for each other, or like we get any of these X over Y, whatever for the different points. And then we're determining a third line that has to pass through all of them, so it should share, given a shared T. So this we can figure out. This is basically the slope. Uh, we have like xv, and an x star in position. Um, Man, not sure which approach I should go further down. I keep stopping this approach because my worksheet keeps stopping. This. Wait, no. Where was I working? I want to see if this one was an improvement. And we have to figure out how. Did you end up getting yesterday's? Yesterday's. If by yesterday's you mean the 24th, technically still today's. Um, Today should be easy. The 25th is always easy. I don't have it yet. And I have two approaches that I'm not sure which I should. I started going down both approaches. And one is to start with a guess and iteratively improve it by like calculating standard deviations and let that inform how far I move my starting position and how much I adjust my slope. And whether I move the starting position or the slope depends on like if all the values are too far off on time or not. And So when I sum all these differences from the average, so like this is a time that x would intersect, right, of a given point, time that y would intersect from a given point. Those three, I subtract them all from the average. So if all the averages are like too low, then I need to do something that make that higher, right? So like here, that's actually not improvement over this 1.38. Um, that makes it worse. We can do two smaller changes. So if it's too far negative, let's try making a small change positive and a small change negative. Let's do like min bound 5 by 10. And we'll bring this one in here for comparison. And for each of these, we're just looking at x. So we're just going to pull out the first parameter. Do you know what approach you're trying? Okay, if it's negative, it seems like increasing it might make it better, right? So let's try some of that. What if I increase it by like that number? The thing is, if you increase it too far, then it starts missing points. So if I increase it by like that number, divide by 2 maybe. Anyway, let's try larger numbers by which to increase it. And that is getting better. If we do just straight up min bound, it's gonna be too much. Yeah, at some point it goes negative again because a bunch of the times will then be negative. And we need to maintain that all the times are positive. So that's tricky. I'm not sure like how much to shift it. And maybe the other thing we should be looking at, like standard deviations. So let's call this standard deviations for each of those. And this will be a tuple, a triple, a three doubles. Yeah, triple three doubles. And x's, we square each of those and then take the square root. So at that square root, x is dot map. Let's see if it gets the idea. That's divided by x is dot size. I don't think you do that. You just square them. And then take the square root. Yeah, that's what we want. Well, xd, yd, zd. Okay, we have standard deviations. And let's look at that. And let's look how changing the velocity changes the standard deviations. Good morning, it's a finale. Blue, Marcus, have you solved Day 24 Part 2 yet? I'm choosing between two approaches here. And one is to like start with a guess, look at the time deltas, and have that inform. So there's like, you could have like let me slow down. Start with a guess, get all the times at which X, Y, and Z intersect with the guess, right? And for a given A, X, Y, and Z might be different. So take the average of those. And then this tells us like, oh, XT might be behind, YT might be ahead, or whatever, because we want them all to be the same. All these values should be the same. So we can calculate like how far they are from that average. And then I can take all the X's and take like how far they are from the average and take the standard deviation of that. and that could inform me like how wide that is. They should all like we want it to be zero. We want it to be zero. Um, but that could inform me how I should change my velocity. And meanwhile, if I take up here, just like the sum of all the differences or whatever, that can inform me how I should change my starting position. I think one or the other of those two. Maybe I'm flip flopping, but something like that. And if I just keep iterating based on whatever these values are, I should eventually get to the right answer. But the thing is, I'm not sure like how much I should iterate based on those results quite yet. So I'm doing some like guess and check experimentation. Um, like another equation solver or doing your own equations here. I'm realizing that I made a mistake here by considering time as well, or like trying to solve for time as well, because now we have all the time free variables. So one, two, three, basically like one per line that we introduce. And then PR and VR are also free, right? Everything else is constants. All these are constants. Um, but that makes it very like we can't solve by just like plugging things back in that way. What I want to plug in is a line. If you have three lines, there's only one line that's going to go all the way through all three of them. So if we have three equations for a line, we can find a line that goes through them, the point at which they go through, and help us determine our t, which honestly doesn't matter because we already have the line. I mean, the t will help us determine the starting position of that line, the p, but this will get us our VR for the rock. Um, so I'm going to do that. So like P1 plus V1, this is an equation. Generally, position of a rock, it's a starting position times the velocity. I guess velocity is going to be our slope. Um, and our P1 becomes our intercept. So those can all just be T, right? I guess we set T equal to whatever our thing is for our rock. Um, well, I don't know. I feel like I'm walking in circles here and getting back into the T1, T2, T3 trap. Um, we really just want to solve for velocities that result in an intersect. Um, no. Which approach should I do? I'm out of time. I have 12 minutes. I'm not going to get it. This is going to be the first time I've not solved an Evan code problem before the next one comes out. It's going to be a big shame. Okay, let me look again at the equations. Yeah, generally x. So these are going to be like x values, y values, z values. And we're going to have like x, y, z values that are going to match. So P basically is saying an equation for one of these lines. Oh, hold on. I hate how my cursor disappears sometimes. Ah, okay, so P equals P0 plus V for whatever that is times a T. Yeah. Okay, I have my cursor again. Um, VT. So here's an equation, and we have We have three equations for a line. How do we differentiate these? Um, we have position for a second line is going to be P0 for one. Let's just assume that this is the P0. So this is P1, V1 times T, right? And then this is P2 um, plus V2 times T. And when we set this like equal to the line for the rock, so the line for the rock is going to equal the starting position for the rock, which we have to determine, plus V for the rock times T. I guess we could solve for PR. Like we set this equal to one of these and solve for PR. In which case, you still need to solve day 21. Somewhere between playing Lego and a Christmas walk. Well, good luck finishing that. Uh, what a shame. What a shame. Okay. Do I do it with the equations or do I do it by... I'm gonna try with the equations a little bit longer. So solving for PR, we have like P1 plus P1T. I guess T is just any point on the line, right? Over wait, is this gonna be subtracting? PR, P1 plus PT minus VR times T minus VR times T. And they're gonna be the same. I guess they have to be the same T. Like this is getting back into what I was doing earlier. I'm walking into a trap. Yeah. Um, Alpha. Wait, it is divided by. Wait, is it not divided by? PR equals P1 plus V1T1 over VR. Oh, it's minus VRT1. Ah, okay, I made a big mistake here, and all that below it is wrong. Minus VRT, these should be the same T. How do we plug others in? Well, will rain stop you from walking? There's also the symmetric form. I mean, we could solve this just for like x's, right? Like what do we do when we're solving for an intersection point between two lines, which we already did. And now we're looking for an intersection line between three lines, right? Yeah. So when we solve for... Yeah, let's kind of copy from this. So def intersect 3. And then there's A hailstone, B hailstone, C hailstone. And it's not going to be a position. not gonna be a position. And you know what? I don't trust that. You want a line, which can be represented by a vector. The option velocity. And it's not even gonna be optional. We're just gonna get it. Okay. And to do some similar stuff. So we get all our coefficients, yeah. And now I guess these are all determined in terms of y. There's no x's. These aren't, they should have like multiple coefficients, I guess, because it's a system of three equations. It can be kind of like this. Um, hmm, this is wrong. This is wrong. 25 is usually not the hardest one. It usually gets a little bit easier. And it's only a one-part problem. Uh, okay, I need to pee before problem 25 comes out. I'll at least try to solve that one quickly. But part 2 on 25, you can only click if you have all the other stars. So I'm going to sacrifice the delta there. Yeah, be right back. All right. It looks like I have to table this. It's a shame. It's a shame. I felt like I had good ideas to approach this, and both still viable. I think I should have just committed to one instead of switching between the two. But we saw 25, and you know what? I feel somewhat warmed up. So we'll see how I do there. Yeah, exactly. You do need all the stars for the last star. Um, day 24, though. I feel like day 24 is not like hard in principle. I should be able to get it. It feels like very doable. Okay, let's go to the calendar. Here we go, day 25. And look at the input first. Okay, an adjacency graph of some sort. Great, we need 100 stars. Someone left a wiring diagram, how the components are connected. Okay, sure. Each line shows the name of the component, colon, list of other components, yada yada. If you disconnect the wire between HFX and PCL, the wire between BVB and CMG, you'll divide the components into two separate disconnected groups. Okay, great. Multiplying the size of these groups, three wires need to disconnect in order to divide the components into two separate groups. Okay, I mean, can we brute force this? Well, edge equals input map. Um, so it's not quite that. We have a node, and then or a component, and then we have listing components. So we'll just call that C's, and then we'll take C to C's dot split on a space dot to list. Yeah, that should work. And do like map dot from, and then this is a what string to list a string. And let's look at input dot size. Oh no, my worksheets are bugging out. Oh yes, the 2023 error code. My worksheets are dead. Oh no, oh no. Okay, I gave myself a check function. Basically, can you reach everything or what's reachable? So reachable from a point. You'd find like a root point. I don't know if these actually form. We can see how many are reachable from one, right? And val components. What can we do? We can do edge dot key set. Actually, you know, I'm gonna be curious about the size of that, and if that's the same as like edge dot values dot flatten dot to set and val components. Oh, we just want components dot size. Yeah, I'm curious if everything also appears on the right side. That'll tell me if there's like a root node or not. But again, my worksheet does not seem to be running. What's it saying? Ignoring declarations for non-active files? Sure, as you should. There we go. Okay, so components dot size, and I want like components dot union edge dot set dot size. So there are so there are some that only appear in the left and some that only appear in the right hand side. So I guess all components would be all components would be the union of these two. Union two sets. Okay. And components, that size, 1507 of those. And presumably, this will only work if you remove like certain connected components. 1500 combinations of 3. Never going to be one of the ones that are only a key. Let's see if we can take the intersection of these two. It's going to be one of these that appear both on the right-hand side and the left-hand side. So we ignore the leaf nodes and we ignore the root-ish nodes. So we take the intersection about links, I guess I'll call them. And we intersect the values button to set. And I want to know links.size. And how many links? Choose three. Choose three might not be too large. I don't know. It's not evaluating. 949. So this is 949 times 948 times 947 divided by 6. That's not bad for brute force. So links dot combinations 3 dot size dot to list dot size. But actually for each of those, I have to check what's reachable from one node. Need a way of checking. Okay, maybe we need to do like smarter analysis of these connection points. Maybe we draw a graph and and analyze it visually and solve by hand. We do have GraphViz now as a tool in our toolbox. Actually, I'll just probably copy paste this and change things. Yeah, let's graph this. Edge.map. And I guess I might want, but we're probably fine. What are we gonna do that for each? That for each case. KV. No, we want to flatten this. So K, we have V's and then V's that for each. We just draw a print line. So a name, another name, and use triple quotes. So we have K and that, and then B. Does that look right? Yeah. And we'll just drop that in Scratch. Many lines. This might be too much for GraphViz. I didn't know there'd be that many. Oh boy. Yeah, it's gonna be too much. Is there no such thing as too much for GraphViz? Well, let us test that. Okay, we have a syntax error. Oh, we need semicolons. God damn it. Can I undo this? Yeah, semicolons. Okay. Nope, that is not different output. Okay, now we can copy a worksheet output, Scratch. Okay. Another syntax error. The dash. I guess the dash is not appropriate. Let's look at their examples that they give us. Um, I mean, I guess I could do a double dash. I thought that was fine for like directed graphs. Yeah, it's like a name. Oh, I guess there are no quotes. You know, before, just to make sure we got the syntax down. Um, let's do a single line or something. It could be the case that there's just no uh, I guess you just need that when there's like numbers or something. So let's just do an arrow and then the name AOE, HTN. So that's not quite right. Oops. Is it really just the arrow itself is not valid? Yeah, okay, I'm doing that. I guess we don't have directions now. Hmm. Oh, there is no direction. Okay. Oh, wait. Oh, it's because my graph is not a digraph? Or are you saying the admin code problem is not a digraph? Okay. Okay, now let's paste this in. So give us a thing, maybe. That's like 3,000 lines. So it's gonna be too much. Mhm. Yeah, can't enlarge. Of course it is. Um, well, that's a waste of time. Um, so we need to look for any point in the graph. Let's draw this out a little bit. So each of these connect to like a bunch of them. There are a bunch of these type of nodes. Um, and I think I'm assuming it's acyclic. That's not actually everything. It's a massive snow producing apparatus. Um, you only have time to disconnect 3 wires. Native components of other components to connect. Connections aren't directional. Okay, so these represent the same thing, same configuration. So there aren't really root nodes. So I mean, I could put that in into my adjacency map, I guess. Um, mm, yeah, I suppose I should. Though the things that look like leaves are in fact not. And basically, I could check. Maybe I can like speed up my check by checking just various. Um, so I guess there's some nodes that look maybe like that, And there is a big tangle of a lot of stuff. I guess it's just a general graph. And we need to be able to split this into two connected components. Wait, isn't there a way to um, like even odd sorting of these? Let's say we just start from one node, and say like what's even and odd. Well, it could be the case that it's not a graph that looks like that. Well, I mean, yeah, because this would be connected there by 2 instead of 3 or whatever. um, finding wires to snip. Do I need like a minimum spanning tree of the graph? And then we need to like remove 3 edges. Let me like, I want to get the degree of all of these nodes. Like maybe there are a few of these in a row with like degree 1 somewhere. And again, it's not directional, so like maybe I should redo my adjacency matrix here. Let's do that real quick. Edge 2. So we have our C's, and we're going to map on each of those. Dot map, or we're going to flat map each of those. Flat map. So we're given a C2, and we're going to get a list of C to C2 and C2 to C. And then this is not a map from from anymore, because what we're going to do, val pairs equals that, all those pairs, and then pairs dot group map _1 _2. I'm gonna just comment all of these out. Don't know when you might want them again. Okay, so that should be like as many as there are nodes. Wait. Group map. Wait, identity. Pairs. There's a list of a list. Oh. I guess we want a flat map up here too. Okay, now pairs is just all those pairs of string and string. Okay, so now we have all those nodes. Just call that edge right now. Okay, we have edge.size. We have edge. I guess we could do like edge.values.map size. I'd be curious about these. Are there any low values? They're all pretty well connected. That sorted, that take 10. Let's just take the 10 worst or sort by. Wait, we have size. I guess we have to two list this. Two list that sorted. Take 10. So if you have a bunch with degree 4, take right 10, sure. And then we have a bunch that are highly connected. So could we take one of those four? Well, if everything is connected to at least four others, so here, 1, 2, 3, 4, right? Then how could cutting 3 lines be sufficient to split this graph? Everything is connected to at least 4. Right. Let's look at the example. I disconnect the wire between HFX and PCL. You divide a component into 2 separate disconnected groups. One with 9 components and one with 6. Um, given a map like this, we could get like the size of that map. I mean, given a component, you can like search through and see what all you get. So we could do like a def connected from a node or a component, yada yada. Yeah. But we don't need that quite yet. Maybe try it. So KLG, for example, connected to KLG, that size. Oh, we need to set that empty. Oh no, that works. What's the issue here? And a set a string, or I'd set, okay. Adjacent to C, and we fold left with C plus C, and then we call recursively. Yeah, that's fine. We don't need like any kind of tail recursion here. I'm not gonna default this to empty. I'm just gonna call it with empty. It contains B already. Then we stop searching there. This gets us a new set, which becomes our new scene set, which we then call recursively. And this is in the wrong order. We need the scene to be on the left side for this to work properly. Okay, so we have that ready. But what I still just don't get. You know what, let me look at this. Maybe I'm like miscounting something. Or you know, let's do edge dot filter vs dot size equals 4. You know, let's collect. And if vs dot size equals 4, return that k. I want to know some of those values. And let's look at edge for MVD. It could be that. So there would be three that we can split, that we can cut, where everything has a degree at least 4. We have something like this, 3 lines, maybe like 3 lines all from the same piece into other parts of the problem, right? Like that could happen. And this connects up there. Um, oh, but in that case, like we could have just cut this. So there's gonna be 3 lines. Yeah, they're not ever gonna be connected to just the same node. Otherwise, it's not gonna be the node. It's gonna be like a node of degree at least 7 if they're connected to the same node. um, can we do like some sort of? I want to do like some sort of coloring of the graph. If everything's connected at degree 4, there could also be something like this. Um, where it's like these are all like very well connected. I guess it could be like any kind of configuration between like what's in one node or the other. Um, Most likely, I think they're going to be like fully separate nodes or whatever. Mm, suppose we could start. Oh, what we could do is start counting a subgraph. So we have a subgraph. We start with 1, and we count like degrees going out of there. So if we start at 1, it's usually going to start with like 4, whatever. And we count all of the edges going out. And then once we find a subgraph where all the edges going out are only 3 in number, then we found one of our components. Okay, I've got it. Def search. Node current. Well, I guess we could also have like a list of nodes. But we could make this. Do you want it BFS this or DFS? Right, if you start going down one rabbit hole, if you want breadth first search this. So we have our subgraph, and this is going to be a set of string. And that subgraph keeps growing. We could have like the boundary, or whatever we're visiting. Visiting can be another set of string. And eventually what we're going to turn is a set of string itself. The subgraph can be cut off in 3. So let's see. We stop if not visiting is empty, because we're not going to get there. I mean, if visiting is 3, then we return the subgraph, because that's like all we have. Maybe just keep adding like one node at a time. No. How do you want to do this? Um, or we could say like if we're visiting that edges out, uh, which I think it works either way. So if visiting that size equals 3, then we just return subgraph. And then our recursion strategy here, visiting flat map adjacent. That's our next visiting. And then we don't add next to subgraph, we should add union visiting. And this does end up being tail recursive. And at first. Okay. Then we search from an arbitrary node. So let's search from set.empty as our subgraph. And then we can start with KLG as our visiting. And the next one is going to be, well, S1. Yeah, the next one is going to be like 4, right? Let's visit at least 4. So we let that run. I guess we would want its size. Before we let run, let's add a size in there. S1.size ends one would be S1.size times edge.size minus S1.size. Or, well, S equals S1.size. We're going to do a variable there. I don't know why. We don't actually need to. How long is this going to take? Getting connected is pretty fast. I think we need to dedupe maybe? I mean, if you take visiting that flat map adjacent, it is still a set. That should dedupe. I have a feeling there's like an infinite recursion here. Visiting should never be 0. Assert visiting that size is not equal to 0. Yeah, I think what might be the case is we are missing that point. They're not all necessarily going to be on the same. Well, hold on. Yeah, we need to add like one at a time. Prioritizing nodes that add a smaller number of new graphs to the set of new. And like this goes in a circle. This goes in a circle. We need to be diffing. Flat map edge dot diff subgraph. Okay, and we fail our assertion because we can't be doing this. We need to do one at a time, so we need to do some sort of like fold left. Okay, so we're gonna do like a fold left recursive call. 1500. We're probably gonna be fine without making this tail recursive, right? So next dot fold left, or Yeah, let's visit a single point. I'm going to find a new search. Visit just a single point. Depth search. Visiting string. Theme is going to be a set string. Sure. We're going to return a set string eventually. And then I can do something like visiting. We add this in. And then we're going to prioritize things that are pretty well connected. If we prioritize anything, let's think about this. So we start here. We're going to visit at least 4, right? So now we have the set of 4. This one's like fully, there's nothing left to explore there. But now each of these has for a bunch of nodes to explore. Let's say how do we make sure we stop at this point here when there's only 3 going out from the entire set? So at each point we count what's going out from the entire set. Not from the entire set because we don't want to like recount this one. So this one's fully exhausted. It's had its things added. So we count all of these are going out to new, right? And then I suppose we use a new one to add. I guess we have like a list of like potential nodes. No, at this point, these are still potential nodes. Okay, let's start over here again. We start here. There are 4 nodes going out. So we can't stop yet. So we have our boundary, our edge, frontier, whatever. We choose one. How do we choose one? And like, what happens if it's connected to one of the others? Then, I mean, that doesn't matter. That's still like one of our potential whatever. So we choose that top one. We're going to list this as a potential. And I guess we count the potentials. So if this connects there, that's also like a potential. This might be connected to 2 more. Oh, no, we don't want full lines. So we haven't chosen yet. Right. So we have a potential to choose. And just draw those in full lines. So like these 5 become our potential. And how do we avoid? So we have the case where like maybe this is one of our connections, this is one of our connections, and this is one of our connections. Let's say we have like this whole part of the graph or whatever, and we get here. How do we avoid accidentally adding this one connection here to the set? We should prioritize ones that are heavily connected to whatever else. We have to add like as few as possible. That this thing keeps growing, right? That could be the case. This is connected to these 2, right? So we're like, okay, let's choose this. It only adds 2 new options. And now there are 1, 2. There's still 5 options. But this added the fewest new options possible. That's what we add next. And then we keep track of this set of options and we choose the best of those. And this would be like an n squared algorithm, I think. So when adding the option that reduces the number of options the most, um, eventually reduces down to 3. So we would not, the thing is, if this is heavily connected in, whatever, then choosing this, I guess if these are already part, like if these are already part of our subgraph, if these are already part of our subgraph, then choosing this would not change our number of options. Oh, it would increase our number of options because this has to be connected to 3 others. So hopefully we will never choose that because that increases our options by 2. So we never prioritize choosing that. Okay, and when options becomes size 3, so we have our subgraph, we have our options, and yeah, we choose from among that. So we have subgraph, which is a set string, and then we have options set string, and then well next is going to be like options dot min by, and hold on, if options dot size equals 3, then we return subgraph, and then we don't do this thing. We're going to choose the best options. So options dot sort by, I guess options could be a list. Like we could sort it and take the head or whatever, or something that's like always, it could just always be sorted. A queue, make that queue, priority queue. Yeah, okay, if we're doing mutable stuff today, import collections dot mutable. Oh, uh, priority. Hold on, I owed about something, but I'm not sure if it's worth owing about yet. This isn't even gonna have. We could call subgraph visit. Val visit equals set. I guess it could be a mutable set. So you have a mutable priority queue and a set. Set not empty of string. And actually, maybe I'll start with like a starting string. Yeah, let's give it a start. So it's just gonna be a set of like KLG. Goal is full now, so I can talk. Yay, graph is. Really? Graph is crapped out for me on this one. Cannot enlarge memory arrays, either one. Actually compile it with total memory higher. I think to use GraphViz, I actually have to yeah. I'd have I'd have to like download and run it. I mean I could try run it in a different client. Let's try editor. Okay, and how does this handle it? Oh boy, it's trying, isn't it? Yeah, I would have to install it to use it. But I also kind of think I've got it. Um, because we're gonna keep a priority of these based on like how much they add. Wait, how much they add, how much they add might change. Hold up, hold up. Maybe I just do it the dumb way of the list first. This is a performance optimization that might not be necessary. Let's copy that. Let's undo some stuff. We'll leave that commented. Hey, don't spoil me yet. Whisper him. um, I think the Eric Wassel answer is there's never an intended solution. No, 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 not quite yet. I mean, I think I have it solved in my head. Val next equals options dot min by um edge. So we take the adjacency and then we diff edge dot diff subgraph dot size, the one that adds the fewest options. And then we search again recursively, subgraph um, plus next. Next is now part of the subgraph, and then options minus next plus there are new options. Well, new options is going to be next, edge next, edge next dot diff subgraph. There's some duplication there. So options minus next, new options. There we go. And that I think should do it. I'm just gonna put in how I get my answer. Val ans 1 equals search set.empty set klg. It knows what I like to start with now. Dot size times edge.size minus not 3. Val s equals there's also that search. And then we'll do s dot size times edge dot size minus s dot size. Okay, let's see if this works. Subgraph. Can't diff by let's just to set that. And then edge to set. Maybe I should just to set it right at the beginning when I parse it. Well, whatever. Let's see if this works, if this is good enough performance-wise. There, I get an answer. 567606. Yeah, I spent too long looking at worrying about like performance possibly. 567606. Okay. Cool, cool, cool. I still had to finish last night's problem. Good stuff. Okay, as 1200. I feel like I could have done a lot faster there, but see how the stars are. Only 170 have finished altogether. I can be one of the first 1000 to finish Avna code if I could just finish this day 24 part 2. Take a look at leaderboards. I think I was the first on the Scala Center leaderboard today. To finish part 1, wait, really? I don't believe that. It's not that. Yeah, a bunch of people have finished part 1. That makes more sense. But why are Silver Stars not showing up? That's weird. Oh wait, this is still showing 24 here. That was my time yesterday. Let me just reload. I guess I was a first, whatever. That doesn't matter. What matters right now is 24. So let me catch up on chat here. Reddit. Oh yes, the mega threads. I've been in there. Um, Barney post Flare tutorial. You have a solver. Yeah. Thing is, like, I want to do this all. One of the goals I set for myself when I first started was doing the standard library, because there are like a lot of other libraries that can help. And this is the first year where I'm sort of extending beyond that rule, and now I can use standard library, but also my own utilities I've written specifically for Evan code. I want to stick to standard library and not necessarily pull out solvers. Now I'm still sort of choosing between two approaches to solve day 24. If people had input, I might appreciate that because I'm not sure what I want to do yet. One was to try and do the math, which I'm apparently struggling with. Um, I think all you need to do to solve this, if you have any of the three hailstone lines, you don't even need to analyze them all. If you have any three hailstone lines, there's only one line that would intersect all three of them. You don't even need to like think about the specific time at which it intersects. Yet, right? Like that will give you the direction vector. So you can solve for the velocity vector just with those three. Oh, we don't even need the precisions. Yeah, given any three velocity vectors, we can solve for the velocity vector. And then given that, we can then look at when it intersects all the times and use that time, or those times, to figure out what the time is of our rock. So three hailstone velocity vectors to get the initial velocity vector of the hailstone. And then for the precision, given the intersect times. Or my other approach I was thinking of was start with a guess, analyze the times at which the x, y, or z of a hailstone would intersect with that guess, and then improve that guess using those times with stuff like standard deviation and averages or whatever. I thought that would be easy. The math is a bit hazier for me here. Like I'm seeing general rules, but there are also like like bounds and limits. Where like if you go too far away, let me see, what was I looking at? There was I have a bunch of graphs here. So this is just like x plotted with time, right? And you could have a very negative x to start your rock and a high positive velocity, and it will eventually intersect with all of these. But your velocity has to be fast enough to catch up with any of these. It has to be like greater than the max velocity. So that's a limit there. And if you get too close, well, you need to stay below, I guess, below the max here. But what I found is if you get too close and it doesn't intersect at all, and not necessarily even at this max, I should double check that. So there are all these limitations. You could shoot from above, you could shoot from below, and of all the combinations of shoot from above, below, or X, Y, and Z, which there be 8, I don't know which one of those 8 is the best to start with as my guess and refine. And of course, the two things I can refine are its precision up and down, which would change all the times by the same delta. So if they all need to be changed, then I would do that. And then if like some are too high, some are too low or whatever, and this is where like maybe standard deviation of all the x's comes into play, I can change the angle by changing the velocity. And I don't even yet know if I can change it so that it's better, but also it's like always strictly better, and it's like better enough that eventually doing all these little iterations will make it correct. Um, have you done interactive 3D visualization of your 24 input yet? Well, I already sort of have an idea of like what that would look like, I think. Right? I mean, because you'd have like a rock going through, and it's like intersecting with a whole bunch of other paths. So I mean, I think if you like looked at that, like you could probably find just by rotating it the point at which all these lines, I mean, even just 3 lines, right? If you do 3 lines, you want to find a line between them, then there's only going to be like one line that goes through them all, right? It has to go through all those lines. Um, so I think that's sort of what it looks like. Uh, is that what you're getting at? Hmm. Right, like just on the x-axis, you can't see how that would look there. But like if you visualize like picking this up all on the y-axis and then like also hitting, it would have to hit all the y-axes. You'd see them all kind of converging on that line. Um, so I haven't 3GS'd it yet. I should really add more visual programming to my toolbox for next year. um, yeah, but I think what I want to do is solve for the velocity vectors. So given I guess you need the starting positions of the rocks. So here, let's look closer at these equations. Um, so P1, this is P1, P2, and P3 being, what were they? Shared positions. So this is like an equation line for the rock, right? And a position at a given time is a rock starting position vector times whatever the time is. And if you set them both to T1, they, or if you set that to T1, that like the time the hailstone one would intersect, then they should be at the same position, right? So you can make this equation here. Um, and trying to solve for, we are really just trying to solve for VR. So like if we solve for PR and set two of these equal to each other, that's sort of something we've tried, except we don't even really want to be thinking about specific time points, right? We want to take time 1 out of the equation 2. So I don't know, if you solve one of those, it'd be like PR equals P1 plus P1 T1 T1 over V. Oh, no, not over. Why do I keep doing that? It's just minus. Minus PR T1. I want a specific time point T1 taken out of this equation though. Um, let's say we were just looking at x's. right? And we have a line y equals mx plus b type form. So the line formed by this hailstone is going to be, oh, I've already drawn that out somewhere. Let me see. Oops. I've already started that for part one. Problem I'm finding is like I don't know. I'm not translating this properly 3 dimensions. Um, what did I do when I actually solved this? Hmm. Well, I'm gonna pull up my equations for a line in 3 dimensions. X minus x0 over B and C, where A and B and C are what? Ah, this is Vx. Okay, so that's our equation for the line in 3D space. And what do we do when we have three of those? We're trying to find a line that, what does it mean for a line to intersect? It'd mean that x, y, z would be the same for all three. So the equation for the line of the rock that we're trying to solve, which should give us our, oh, I guess there's this 0. We don't have the x0 for the rock. um, yeah, we just set them all equal. Parametric form for t for each of x, y, and z. This is just like the y equals mx plus b. So yeah, let's just do that for basically all of the rocks. So we're gonna have 3 rocks. We'll call them. You just call them 1, 2, and 3. And let's like do do the x line for rock 1, right? So that's gonna be x, and again, it's gonna look like this is gonna come from the p. So we'll say x1 because it's the starting position, the starting x of rock 1. Plus time and being the x velocity. So this is velocity 1. So x equals x1 plus time times velocity 1. Right, and then we have this for all of them. X2 or time times velocity 2. And these are all constants. Well, constant, not the time. So if we were set like x to be equal between these two, we want, wait, do we want x to be equal between 2 lines in space? I don't think we do. That's the intersection of those 2 lines. We want that x to be equal to some point on the rock. Oh, right, and that helps us get rid of like the x rock So here's for the rock, the equation. XR. Oh, Eric Bossel. Yes, go pass out. I'm sure it's been uh, quite a month for you. You need your sleep. But thanks for the good luck. And thank you so much for having the code. It was a lot of fun. R. So to get VR, in such a way that we can ignore XR, I guess I can't really just ignore XR, can I? Yeah, that determines where. Um, okay, so we have three of these equations, and how many variables? They're all written in terms of time. I mean, we could go to the symmetric form, x minus x0. We could call this x of 1, and then vx of 1. Um, I don't know how to solve for this. Y minus y1, and then vy1. Uh, there's like a y and there's an x in there. And then equals yada yada, etc. for z. And these are all constant values. They are all restrictions on x. So these form restrictions on x, y, and z that we can then plug in to our main line. Because at these points should be on the line. No, not x0 and v0. It is given that time. The thing is, when we bring time into the equation, there are just too many free variables, right? Let's go back to this here. We want to solve for PR and VR. I just need to wrap my head around the equation of the line in 3 dimensions. Uh, there are an infinite number of lines that go through 2 lines, but once you add like a third line that must go through, now you have to find three values for t. And 3 values for this. There are 3 values for t, which correlate with 3 different intersection points. We're not trying to solve for those intersection points. We really just need the times. The times can help us solve for, right? How do we solve for T1? I need something that relates all three of these T's somehow. Um, these three T's all describe points on our PR rock, right? These 3 points, P1, P2, and P3. When this is done, I think I will want to go back to this approach here, guess and improve the guess. But I think I'm on to something. Where did I have like my minimum maximum times? Here. So whatever we're guessing, it has to be outside of this range for precision and outside this range for velocity. And it has to be outside in the same direction. Right, if there's a low position, then you need to have a high velocity, except I wasn't finding that in practice down here when I count my positive time differences, which maybe I was, what my time, how did I calculate times? Yeah, these are my intersection times, and if they're negative, it's in the past. And we don't want negative intersection times. We go back to this for a sec. We have 3 points on the line, each of which are restricted by their respective hailstones, velocity, and whatever. Yeah, I've been trying to get rid of the T's. And I've been struggling with that. Actually, you know what? One approach that I gave up on wasn't even correct. Because I made a mistake in some of my algebra. So I could do something like that again. I don't know, let's take let's take these. And I'm gonna try again to remove the T's. Try elsewhere. Mm, I swear this is so counterintuitive. This whiteboard, I mean. Okay. Do something with division. Do I have a pen? Right, you can't divide the vectors. Yeah. So, 'cause, I take like one of these equations with a rock? Um, well, hold on. Thing is, each intersection point being described has its unique t. And if I could try to do this in terms of, okay, so these are my two constants. I want to do things in terms of those as much as possible. If I solve one of these for like PR and then set two of these that are equal to PR um, equal to each other, um, I could pull out T1. Okay, you know what, let's try this. Let's say T1 plus B1 T1 minus BR T1 equals something similar for 2. Right now we're just solving for the velocity. So we have V2 plus V2 T2 minus BR T2. If I do start dividing, we're basically pretending that I'm turning V into, or these P's into X's, just their X components. Okay, and we could pull out T1s in here and T2s separately. V1 minus VR. V1 is a constant, so that's nice. Equals P2 plus T2 times V2 minus VR. Pulling in P3 doesn't feel, pulling in the third equation doesn't feel helpful because it just brings us another time variable. What if we figure out, I mean, what happens when these two are like at the same time? I don't think that's a helpful point. Yeah, I can solve this for T1. I think I did something like that in the past. Right, if I were to solve this for T1, what would we have? So I'll just do it again just to make sure I'm not making any mistakes. So we have this equation. I'm just gonna try and do a lot of this in my head. I'll try to keep VR positive. So T1, there's gonna be a division down here Oh, you know what? Let's avoid the division for now. And we're gonna say T1, what are the factors? We have VR minus the V1 from the other side equals P1 minus VR. Um, and again, these are vectors. So basically for all of these T's, Tn, let's just start using n so we don't have to draw three lines of the same thing. Pn minus Pr. I've written this code, I've written this somewhere. Actually, I wrote this as code, Scala. Up here, I was getting the times, the time of intersect for all of these. Where is it? Yeah, it's exactly the same thing. VR. And yeah, I'd done it separately for each coordinate. So like this gets you a triple of times. And what do we know about that triple of times? VR minus V1. Well, we want those triple of times to all be the same, right? They all need to be the same, hence this whatever equals Tn. And I guess this gives me restrictions on VR and on whatever the rock ones, VR and PR, right? Those T-less expressions are all equal. Um, wait. You're You're right. Because well, hold on. No, I mean, let's say the first rock intersects at 5 seconds, right? Then we would want this to be 5 seconds for each of X, Y, and Z. So we can't like set that equal to we can't set that equal to another Tn, right? Because like the other intersection point might be 3. Right. I'm okay, I believe you because you're saying it and you've already solved it. I'm not believing you because I don't know how that's true yet. You see that? Oh yes, yes. The X, Y, and Z should be equal. Yeah. Okay. I get you. I get you. Yeah, that's exactly this stuff here. I want all of these to be equal. That's why I take the average of them down here and I subtract them from the average because I'm checking how far off they are. And this is supposed to be my metric that I use to evaluate how good a guess is and like iterate and improve upon that guess. I mean these in sum, like you know, the values for all the other. Yeah, you mean that, not across times. Um, oh yeah, yeah, equations for the line without t's. Oh, okay, yes, exactly. I see what you mean. Yeah, so the equation for the first line is that triple is this triple equality, right? Where let's say x1 minus xr, we call it xr, right? And then Vx of r, yeah, let's say Vx of r minus Vx of 1. Yeah, so that's an equation without t's. You're right. You're right. This triple equality makes me feel weird though, but I can work with that. I guess we could use like the x of one and the y of another. Um, let's like solve one of these for xr and then plug it in. Keep chugging. Yeah, just keep chugging using the other three equations. Um, so let's get xr, and we could do this in terms of like the y's for 1. And let's see if we don't hit some dead end there. So xr, we're gonna have to negate something big, so we're gonna multiply this over on this side. Oh, that's gonna have an xr too. I'm just gonna write out the full thing. So delete that. We're gonna fill this in. So we have y1 minus yr and vyr minus vy1. And we could use that to solve for one of these values. I'm going to multiply across first, or I'm going to multiply across my head. So we have this. And, these are all like subtraction whatevers. And both of these have, well, there's like an xr, there's a yr. Oh, we can only solve for one of those right now. So let's solve for like xr. Rather solve for the ones that are positive. Yeah, exactly. I'll just use x and y. You're right. You're too stupid to implement min-cut by myself using graph library. Yeah, Z3 graph libraries. Min-cut. Is that what this is called? This minimizing thing? Oh wait, yes, Brett, you were telling me about minimizing. Yeah, I started down that path. So when I started working on problem 24 today, I decided, okay, there's two approaches I could take. I could try just plug in 3 of the points and like solve an equation, or I could do this and start with a guess, right? I have a guess. I take all the times. I compute a lot of different stats on this. So like there's the standard deviation of all like the X time deviations from their own average there or whatever, right? And I've been experimenting a little like, okay, how much I need to change X position given, given some value here, or like how far away all the X's are in general, right? And I was thinking about, okay, I can just iteratively keep improving the guess. And here's like an example where I'm like working through iterating on that, and it's getting better. You can see it getting better. But there's some point of like diminishing returns. And I think that's the point at which, yeah, like right there, that's the point at which like you get, well, I guess you're too close. X opposition dot x plus min bound over 2. The thing is, it's still before all the points. So I don't know why there isn't some sort of intersection and why we have so many negative intersections. I guess it's negative with respect to the others. And of course, it would depend on the velocity. No. The sum shouldn't depend on the velocity, just their like spread. right? Oh, wait, wait, wait. Min cuts. Okay, yeah. I think I did that for this was easy. It was just this is my algorithm right here. We have an adjacency graph and we keep adding 1 point until like the boundary is 3. It took me like a little while to get there. Um had a few false starts, but I got it. Yeah, today's was not bad. I feel like I should have been faster. Um I got 1200. That's close to 1000. As good as I was doing last year, I thought this year I'd be able to get like under 1000 every day. But I didn't practice. I haven't practiced. I'm super rusty. And last year I was practicing a lot before admin code. Um, but what you're saying above is solve an expression that only depends on the rock. Don't solve for a variable. Um, yes, I, right. Like, well, you mean don't solve for the things that are constants, right? The hailstones, because the y1 is already determined. Wait, y1 being what exactly? It came from the p. Yeah, yeah. Y is the starting position of rock 1, or starting y position of rock 1. Anyway, I'm gonna go back to solving this because I'm not sure how to like minimize and improve my guess eventually, but eventually I do want to try. Oh, not that. I do want to try this approach here, and maybe solving it this way will give me some insight to it that way. So you had the subtraction, you had subtraction. I want to start for by solving for VR. So VR, I'm gonna move to this side. All right, so VXR. Maybe we just solve for VXR. So VXR shows up here, and there's this minus, and then I guess we have this whole multiplication thing, um, which is a little bit annoying. VXR minus VX1. Okay, I mean that's a constant. That's a constant. Y1 minus YR. I guess we have to multiply this across before we know how to pull out the VR. So let's see. We have VXR times Y1. um, how did you? So I didn't have Graphviz downloaded. I think that's part of what part of why the problem took me too long was I spent too long generating the Graphviz and then like I was trying to put it in online, and of course it's too big for online. And I was like, you know what, I can just solve this. So I solved it. But I wasted time trying to put it on online. I didn't want to download and install it right now. But sounds like I should have it installed generally. Okay, what happened here? Okay, we have V, VXR, times what? Y1. Y1. And then we have minus VXR times YR. And then we have two more factors in there. I guess we have minus VX1 times times. I think at some point I should just be writing this down in code. It's easier to type it than it is to draw it. But let's continue this. We'll complete this. So vx1 times y1, and then there's gonna be a plus vx1 times yr. And solve for vxr, we basically just moved all of these onto the other side. We have a whole bunch of things we're multiplying, and then we divide them all by y1. And then all those things we're multiplying still have unknowns, right? Because we have the y from the rock, so we need like a value for yr. I'm just gonna highlight in green the things that are. So there are still these three variables. We're solving for vxr. We have xr and we have yr. So we could take another equation and solve for yr and then plug that in. I would write out both sides without solving, since I don't think you need to divide. Oh. Okay, yeah, might not need to divide then. Oh, right. Uh, well, I mean, I was thinking if I move this stuff over. Oh, wait, y1 is a constant. Hmm. Okay. Let's write this up, boy. You know what? I think I should switch. I should switch this to code. It's just gonna be like easier to edit, easier to write, etc. The xr times yr only depends on the rock. Yes. Oh, like keep a term that only depends on like this one right here. Oh, right, I forgot I had that v. I forgot I had that here, so we can't just solve for that. But this depends only on the rock, and I could pull that out of another equation. I see what you're saying. Okay. But also I'm gonna switch to text because that's getting messy. um, you'll get one term like that on the left too. You can equate across rocks. Yes. I see what you're saying. And you know what? If I'm writing in here, Copilot will help me keep my equations sane. So we have x1 minus xr over vxr minus wait, no, vxr minus vx1 equals y1 yr. Okay, it seems to know what I'm doing there. And then I'm just gonna rewrite this by moving the denominators. So we're gonna do vyr minus, okay, great. Look how much easier that is with Copilot. It's checking my algebra as I go. And then now we might have something similar for like twos. So we could do twos with, should I also do it with x and y? So there's a term. Wait, what depends only on the rock? Oh wait, I should multiply that out. Um, so vy vyr times x1 multiplied out. Okay. Ah. Yes, it expands the products for me and everything. Look at that. Look at that. That's uh that's beautiful. That's so helpful. Uh, okay. Yeah, I should have moved there from the whiteboard earlier because that's just too much writing. Okay, so now which of these contains an R, or which of these contains like two R's? Let's say we want just this term, vyr and xr, or what's another potential? Yr and vrxr. Okay, do v, or yeah, let's just do vyr times xr equals, I trust that. And then now we're going to do something similar for, let's say x2, just x2, and we'll use the y's because we're using vyr and xr. Oh, we have to use x's and the y's. Okay, so x2, x2, y2, y2. And then now we have vyr. I wonder if we can go that far ahead. That's not quite what I want. Okay, let's just do the same thing, the same steps. There we go. Okay, great, great, great. Now we can take these two as equal to each other and find another term to get out. Line 251 looks wrong to you? Okay, vyr xr. Yeah, you're right. This should be negative. Um, I'm gonna do that purely manually, and then Copilot should learn from that, right? Um, so if we move this to the other side, it becomes a plus, because I want it to be positive. Plus that. Oops. So plus that. Take it out from this side. And then this stuff, subtract from the other side. And then let's have vyr times xr equals, let's see if it gets that right. Okay, it's just flip-flop the equation. And now vyr times xr equals, but it's there, it flipped all the signs. Okay, now that's correct. Okay, let's see if we can follow that pattern. Plus vyr xr, yep. 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 Cool. Okay, now let's see what terms that depend only on the rock are here that we can remove. So we have that equals this. Oh my god, I would hate to be doing this by hand. Think I should have YRVXR on the right too. Let's see, I don't know how old that message is. Do you think it's correct now? Okay, is there a way to simplify this? Let's look for the R's, and maybe there's a term that has two R's. V by R, XR, V by R times XR. What I have now is fine. Cool, cool, cool. Let's look for something with two R's in here. YR, VXR. And then YR, VXR. YR, VXR shows up on both sides of this. Wait, YR, VXR, so we can remove that, I guess. So we can remove this plus YR, VXR, and remove this YR, VXR. Wait, aren't there gonna be just too many terms that are the same here? Yeah, okay. Look at everything that cancels. Look for more R's. I wish I had this with like LaTeX rendering too. Let's say this. Then we cancel out more. It didn't cancel out anything. Okay. Some of these are like purely constants. So let's, where else does VYR appear? VYR times x2, VYR times x1. I guess we could solve for VYR. I don't need any more canceling. Okay, cool. Yeah, it doesn't look like more canceling is possible. The VYR appears on both sides here. I want to write the equation in terms of that. Okay, if I did this for like two other things, then I suppose maybe I could cancel out I could fill in VOIR and remove these. Wait, VYR, what else is R here? We have VXR. And we just have straight up XR and YR. That's just linear algebra since you can use more rocks. My linear programming is super rusty. Sorry to disappoint, but this might be more manual than that. But maybe I could see where like the vectors are here. I guess we could do the same thing with other rock values, right? We could get another thing like this. There's no built-in linear algebra library. There are linear algebra libraries. I haven't imported any libraries while doing admin code, just a standard library. And that's kind of been like a limit for myself to do everything just using a standard library. Like no Z3, no constraint solvers or math libraries. I did loosen that restriction a little bit this year. So this year, I allowed myself to write my own library for admin code stuff. like common classes and utilities or whatever. And in the past years, I always wrote everything completely from scratch. So if I made a point class, I made it just for that file. Okay, so we could do the same process for other rocks and other kinds of variables, right? So like bringing in z's. I don't think we want to bring in z's yet, but maybe threes, right? So the same thing would hold for if we replace all the ones with threes, right? Replace one with three. And not that. Okay, so we have these two equations. What's common between these two that we can then yeah, I was never gonna do this by hand on the whiteboard. Jesus. Um yeah, these will all share a bunch of like y terms. So we put all or I mean two terms. So we put all the two terms on one side, which they actually already are. Oh, this isn't helpful. I'm just sort of going in circles here. Um Let me see if I can one next one. How many terms are there? There's six terms on each side. um if I did this for I could like replace these with z's and we'd have like x's on oh I suppose there was another way to do this, right? So we had removed vyr xr from each of these, but there are other terms that had two parts rock, right? So up here we could have chosen so vy. What else has two r's? And maybe we can try to like remove out those terms. YR, VXR, that's what we removed. Wait, VYR, VYRXR. Hold on, VYRXR, YRVXR. YRVXR continued showing up until we were able to cancel it out by setting two of these equal to each other. So we got rid of both terms that depended only on the rock. Um, Linear solve. So solving a linear equation. I guess each of these has a single r term. I guess some of these are constants. Just to make it simpler for my brain, I'm gonna just move all the constants over to like one side. So let's take that out. BYR. This has an XR. This has an R. This is just ones. So we're gonna subtract that. This has a R. Back from that side. This has no R. says an R. Isn't misguided, is it? It says an R. Wait, isn't that just what I just moved? No, this is Y2 VXR. Hmm. And then we have an equation of four variables equaling a constant. Are there no more R's here? Oh, there's one more. So we're going to turn this into an add. Okay. So this has four variables in it, right? It has VYR, which appears twice. We have VXR, which appears twice. And then we have XR, and then we have YR. Wait, XR appears, yeah, XR appears twice, and then YR appears twice. And each of these appears with a constant. Kind of want to like put the constants first. Um, okay, I'm gonna pull out the R parts. So VYR times x1 minus x2. Hey, this is looking better, right? VYR did appear twice. The other time it appeared. Just check that. Yeah, minus x2, VY1. Okay, that's looking better. And now we can get a few more things like this. How many more? So we have four variables, so you need like four more of these in order to Let's gonna move this over. For no real reason, I just didn't want negative leading. So we have the velocity, the y velocities, and we have the y velocities and the y positions. So we can do another equation for x velocities and x positions. Another equation thing is, as I keep adding, if I add more equation, then just like do this for z or whatever. Do we get another set of constants that this should be equal to? So the same thing should be true if we'd replace like 2 with 3, right? 2 with 3. Oops. 2 with 3. 1, 2, 3, 4, 5, and 6. Two different equations, two different constants, sure, whatever. We could have also done that with like z's. We guess 4 of these. Can we just solve for VIR in one of them? Use that to plug in. Right, it'd be pretty easy to move stuff over. um, and actually, is this actually ones, threes and ones? I mean, what if I like replaced 1 with 3? That's like another equation, but I have a feeling that's not actually helpful. Basically, given the x and y, given 2 rocks, we can get this relationship, or 2 hailstones, we can get this relationship that tells us something about the rocks. Oh wait, interestingly here, there's this. Where did this XR minus XR come from? This looks like it might be wrong. BY1 times XR minus XR, that's a 0. Wait, no, where's the XR? XR. Does VY1 even appear twice in the top line? This is wrong. This line is wrong. Want to formulate as A times XB, where A is a matrix of known values, X is a column of the unknowns. Okay, okay. Yes, I should do something like that. Then you can matrix solve. It will have to be like some sort of matrix solving by hand. I don't have a matrix library. Rock times rock parameter. Yes, I'm trying to organize in that way. But like this is wrong. I think this whole thing is kind of wrong. Okay, so VYR. Let's make the first edit here to be to put like the VYRs, juxtapose those. So VYR, here we go. Put that up here. So that's a rock term. There's another XR. And somehow it like had screwed up some of this. So now we have Y2. Let's do it this way. EXR. You're right. I'm just like scared of linear algebra. So now this is VYR times x1 minus x2. Still wrong about this. So this is XR times VY1 minus VY2. That's not Y2. That's supposed to be VXR times Y2 minus Y1. And YR. No, that's not YR. Why is it so wrong? VXR times YR minus. No, minus Y1. Y1 minus Y2. And let me double check that because Copilot seems drunk. By1 minus by2, cool. Y2 minus y1, cool. And this last one, vxr, it's going to be, no, yr. Yr is on the outside. Yr, vx2 minus vx1. Okay. And let's order this properly. So these two become a vector of variables. Okay, I do Gaussian elimination by hand. And I'm gonna look it up because I'm musty. So XR, VXR, I'm gonna reorder these a little bit. So let's do XR and VXR, and then YR and VYR. Okay. Okay, so we have, yeah, the difference between these two. I really hope all the positives and negatives out there are right. Oops. I'm just gonna just negative over. Um, I just want to like organize these so I see patterns. Y2VX2 minus Y, okay, whatever. And we can do some reading. Okay, wait one sec. Algorithm for solving systems of linear equations. Yeah. Row-wise operations performed on the corresponding matrix of coefficients. So we have matrix coefficients here. And then XR, VXR, YR, VYR is our vector of things we're trying to solve. Compute the rank of matrix, determinant of the square matrix, blah, blah, blah. Modify the matrix until the lower left-hand corner of the matrix is filled with zeros as much as possible. Okay, so we can swap two rows, multiply a row, add a multiple of one row onto another, turning lower left into 0. But this won't allow us to solve everything, right? Like we'll need to do this again with like threes and z's. Okay, example of the algorithm. Here we have a system of linear equations. I did do this by hand in school, but like again, that's been a while too. Describe says so 2x plus y minus z equals 8. Sure. Oh. Except I only have one equation right now, right? Unless this is describing a system of, no, it's not. Okay, system of equations. Here's the matrix. These are the coefficients on the left. And okay, and we take a row operation. In this case, we multiply by -11 or divide by, wait, hold on, what's going on here actually? Um, row operation is L2 plus 3 halves of L1. Okay, yeah. Um, and basically we need more rows. Let's get more rows. Okay, so we can do this with 3 in place of 2, right? We could done this whole thing with 3. 1, 2, 3, 4, 5, 6, 7, 8. We still have 4 variables. We could have done this whole thing 3 instead of 1. Um, if we start to do this with z, yeah, we're gonna lose our x, and we have 1, 2, we have 1, 3, and we have 3, 2. That seems like all we can have right now, right? But there are four variables. So don't we need more rows? Okay, so this is where we do Gaussian elimination, and we're trying to eliminate some of these rows, and we can't do this without actually knowing the actual values of this, right? We want zeros in the bottom, vy1 minus vy2, vy3 minus vy2. Yeah, so I need a fourth row, but I'm not sure where I'd get a fourth row. I mean, could I do it in some way? Like, what only shows up in... I can't just sort of replace all the z's with y's. I guess I have to come up with more equations by doing this whole process again for other... I mean, if I do this whole process, this is the kind of equation I get, right? I suppose... So, I mean, we have, all in all, we have like 12 unknowns. We have 12 unknowns? We have 8 unknowns. No. Wait, we just have 6 unknowns. Yeah. XR, YR, ZR, and then VXR, whatever it is, VXR, VYR, and VZR. So we would need 6 rows, and that we can do. So let's just replace all of the y's with z's here for one. We could have done this whole process with y's instead of z's. So y with z. Okay. Now we have ZR and VZR. So now we have six unknowns and we have six equations, right? Six unknowns, six VZR, um, the other Z stuff, and we have ZR. Okay, but now these variables aren't all necessarily lined up. I think we probably have to have like a big zero in the space, don't we? Right? Yeah, if you're drawing that in a matrix. Um, yeah, yeah, we do. Um, let's do some multi-line. Okay, and now we can fill in these noise values and do some Gaussian elimination by hand. I think we need to have actual values to do the Gaussian elimination, don't we? Otherwise, how do we like set any of those to zero? So we start with the bottom. We're trying to eliminate the bottom row, get as many zeros there as possible. Let's start by trying to eliminate this. And I guess like we could subtract the first row multiplied by something that would make these two terms equal. And what would that be? Um, I guess the reciprocal. So we could multiply the first row by Vy1 minus Vy2 over Vz3 minus Vz2. So if you multiply the first row by that and then subtract it from the bottom row, and those are just constants. Yeah, you're right. It's gonna be a nightmare symbolically. This might be a point. The thing is, the numbers are huge too, and I don't want to like draw all the numbers, but uh, you're right. You're right. Maybe do this in an Excel sheet. Oh, and at this point, like I can also take out the variables, right? I can just straight up put in numbers here. And you know what I could do here in the REPL? We could assign like values R1. We could do a bunch of tuples or like lists, right? We could do a bunch of lists, and to subtract row one, we could just like multiply everything in that list by the appropriate thing. This might be a time to go back to writing code. Yeah. You mean like write code that does the Gaussian elimination? Yeah, yeah, you're right. So we have a matrix. Let's just define a matrix. Um, let's take three arbitrary hailstones. So val, you know what, we're gonna give all of these values names. So val hs1 equals hailstones. Let's take let's take 13. Val hs2 equals hailstones. 243, sure. Val hs2, we'll make that 3. Equals hailstones, 182. And like hopefully like those aren't, none of those are like parallel with each other. Just look at the velocities real quick. Um, eh, I can always change. I can always change those values. Let's get these names and we'll put them into a matrix. Um, well, VY1. And then Copilot's going to be able to get this pattern. Yeah, let's start with X. Val X1 equals hs1.precision.x. Val Y1, sure. Val Z1. Val VZ1. Okay, getting this. Oh, okay, now we do the twos. And for that, we can just copy paste. And the threes, we have 2 and we have 3. So all of those have values now. And now matrix, val matrix equals a vector of vectors. So I'm going to scroll up here. And move, I'm going to copy the comment up here. And maybe you'll figure that out eventually. Actually, I'm gonna modify this. He just wanted my copy paste. Oh yes, good catch. Okay, there's 2 and there's 3. Okay, and I'm gonna make these comma separated. In fact, actually, this directly turns into my vector, doesn't it? Let's do that. Vector of that value. Then that value. And then we remove these pluses again. And then our alignment breaks. We can fix that. So there are two more zeros here. Zero. Oh, and then there's the other side of the equation. Let's add those in too. All of that. And to do this properly, I might need to switch away from doubles. I just too long all of those. Actually, you know what? I don't think there was there even enough space for that full long double? I mean, it's just E14. So there should be enough space as long as it's not to the maximum value double of long. So we got too long all of those. Okay. Matrix vector of all of these things. Let's add some commas at the end. And we'll still put these separate so we can actually just see the values easily. Yeah, this thing that's not really defined anymore. Okay. Now we have some operations to do. Make the bottom 0, starting with the bottom left. So whatever value is in here, we can subtract something from the top. Well, okay, let's look at our operations. What operations are legal? How do we choose between them? Swap the positions of two rows. Multiply a row by a non-zero scalar, and add to one row a scalar multiple of another. I could model each of those operations. And we figure out like what turns things into zeros. I mean, one of the easiest things to turn to zeros would be, I guess, these. Wait, hold on. Yeah, let's look at these where there are already zero rows, because that might be like an easier constraint to handle. Let's see. Well, we're not going to subtract a row from itself. We can subtract some multiple of this from this row. And it would be like based on this right here. Let's give these all names. On algorithm though, you want to loop through the columns and loop down the unsolved rows. Okay, yeah, we're not gonna do it by hand completely. This is by hand enough. Okay, let's think. So these are all unsolved rows. Let's look at the description of the algorithm. Suppose the goal is to find and describe the set of solutions to following whatever. Okay. And we're trying to remove this 2x from the bottom. So what we do is, I guess there's multiple things we could do to get rid of that 2x from the bottom. The most straightforward way is just to subtract the top row. What did they end up doing here? L2, oh, I guess they solved both of these. So L3, you add L1. Great. It could always just be like add the appropriate multiple of L1 that will delete that. Always though? Oh, well, not always. Because if we keep doing that, then it will undo eventually. So we could start by adding like we have to figure out how to get this next one to 0 without changing this one, without changing the first column. All right, so our next goal here. Oh, okay. We take the second row. L3 plus minus 4 L2. Oh, okay. Yes. For each of the columns, we can we can keep choosing the next row. So it's gonna be something for L2. And then now, yeah. So for the first column, we just take the first row and we take all those columns and add the appropriate multiple. And then for the second column, okay. So, well, Gaussian elimination. Oh, I thought that was a spelling error. I rewrote it. Okay, matrix, the vector of long. And what we're looking for is just a final vector of long. And then I guess these are the rows. We can get the columns, but columns equals matrix dot transpose. If you're okay, fair enough. I see Black Deep walking me through Gaussian elimination. Thank you very much. Okay. So, I kind of want to do this cursively instead of iteratively. Right, so first we're removing column to remove. So there's a call int. And basically, for that column, we'd use row 1 to remove everything. Because I don't want to keep making... This is not a mutable vector. Maybe I should make this... I'm gonna use a mutable array. That'll make it easier to handle. Array of an array of long. And then what we want is an array of long. And for m is down, n is across, n by n matrix. Yeah. So for m in matrix, dot indices. These are gonna be rows. It's is it square? There are six. There are seven. There are seven across. So matrix dot head dot indices. You know what? I'm gonna use row and column so I don't confuse myself. Or for column. Yeah, for column and matrix dot head dot indices. We're gonna do stuff. Do this matrix. um, It's gonna be like a column index, sure. And then we're gonna take our first row, I guess the one of the same index. Val row equals uh, matrix call. Okay. And then for call plus one until matrix dot length. Yeah. Cool, cool, cool. Glad I'm on the right track. um, Wait, for what's this gonna be? I guess row index. I think we're just gonna add full row. You know, I think I need to use M and N. Let's just make sure. I have those right in my head. M by N. Okay, so for N. And then here, matrix N. That's the whole row. And for, I guess we want indices of rows that we're gonna add. So we're gonna get M in column plus one until matrix dot length. Factor. No, that's probably correct initially. So here's the other row which we're going to try and eliminate the, the first element of. So the factor is row 2 n, right, divided by row yes. And then for each of these k's and until I kind of like to just add the whole row up, but whatever. So row 2k. I think we just take our original matrix. I want to take our original matrix. Matrix mk minus equals matrix nk times the factor. M being the row, the one we're eliminating. A being the just all the columns. And N here is the pivot, row. So we do that, and we do that over and over again. I think that's it. And then we can do some asserts. So now it's going to be matrix.head is what we're returning. But we can do matrix.tail dot reach row, assert row dot for all equals 0. And this is a def. Starting at k assumes columns less than n are 0. Yes. Yeah. uh, wait, what's the issue here? Double definition of matrix. Wait, not found call. Oh, right. M or n rather. Okay, and now we do the Gaussian elimination of matrix.map to array to array. If that runs all right. If did by 0. Okay. Right. Right here. If row n is 0. Yeah, if row n is 0, we have to do something else. So that's a case like so here. Let me think about when we get there. So we start in the bomb latch where like we add multiples to the first row, and these all become 0 here. And then we go here, we're adding multiples of the second row, and these all become zeros. Well, if I just did something, well, we'll get there when we get there. And then we get third row, this is already 0. So we don't have to do anything, right? So we need like an if, an if check here. So mn row t equals matrix m, sure. And this is when we do that whole, this is adding the rows. We have an if. Is it just matrix mn is not equal to 0? Let me think about that. So for a row which we're going to try root eliminate from, if mn is not already 0, then there's no need to do anything. And then we're looking at row n. The row is matrix m. We still have the div by 0 problem. But that seems like, that still seems like a good check, right? We still don't need to do that. And if row n is 0, so row, the nth element. Oh, no. I think we want if row n is not equal to 0. Hold on. No, row 2m. So it is matrix mn. In fact, we can put this check down lower, right? So if row n is not equal to 0, then we do all of this stuff. or rather row 2n. Well, hold on, what's row? Oh, hold on, that's this up here. Okay, so that check I added is still a good check. It's just going to result in nothing happening because row 2n is going to be 0. The factor is going to be 0. Um, so that check is fine. We don't even need to change anything because that's just going to be 0. But if the value up here is 0, then we can't multiply it to add below. And once we get here, I hate the hovers right now. So 1, 2, 3, 4. We're in the 5th column, and I guess at this point we'd be using the 5th row, which is not going to be 0. Not 0. Row n is going to be 0 when the row so basically no zeros along the diagonal. So that's happening sooner. That's happening here. That's where it's getting me. 0, 0. Oh, it's happening here too. Wait, no. 2 over 3 and 3, 4 and 4. It's happening right here. This is a problematic 0. So we get to row, we get to n equals 3. Start implementing pivoting. What is that, like switching rows around? Okay, yeah. Back to the Wiki article. Back to the Wikipedia article. But wait, let me see if I can figure out myself first before I look into that. So on row 3, there's nothing to subtract. What are my operations that we have? So what we've been doing is just get a multiple of another. We could also swap the positions of 2 rows. I'll multiply a row by a non-zero scalar. What I could do is pre-swap the positions of rows so that I don't run into that issue. Right, like if I just swap these 2 around, wouldn't that disappear? I think so. There, I implemented pivoting. No? Okay, I still did by 0. Let's do this. If row n equals 0, then we're going to print line mn. Whoops. I want to interpolate that. M and n. Dividing by row n can still divide by 0. And in this case up here, you mean? I can't just like reorganize these. Oh, right. It could still end up going down to 0. I mean, what if I just did like more swaps and kept trying? Okay, we have an issue at 4, 3. 0, 1, 2, 3, 4, and third column. Oh, right here. Yes, we don't want that to be a 0. Um, Now we have 5, 4. Um, the very last one. Oh, and there's a 0 here. Do that. Then we hit this 4, 3, don't we? 5, 4. No? Okay, all the diagonals are not 0. 4, 3. 0, 1, 2, 3, 4. And then this third column. Wait, this might not be possible. Okay, so like this definitely needs to be there. But then now 5. Oh, am I doing this too many times? I think I'm doing this too many times. For n, we need to drop right 1. That we don't hit that 5. We should never hit 5. Oh wait, that's still 4 on n. So that happens beforehand. Row n, 0, 1, 2, 3, 4, 5. Me think of this. Okay, so we start with column 0. Right, we start with the first column. We do all of that. Second column, we're using the second row. Third column, we're using the third row. Fourth column, we're using the fourth row. And fifth column, we're using the fifth row. And do we get to a sixth column? It's just, yeah, there's nothing on the sixth column. We should still drop right 1 here. Not wrong there, am I? And now 5, 4 is still problematic. 5, 1, 2, 3, 4. This one here. Why would this be used as the row with which we are? Oh, hold on. The matrix width is even longer. We need to drop 2 because we still have the answers column. Okay, fine. We go back to Wikipedia. Just check things. This is take it back to 3, 4. Yeah. Unfortunate. At this point, I don't even remember what the original was. Wait, that should be even worse, right? No, it's still 5, 4. 0, 0. Okay. We go back to Wikipedia. Swap the positions of 2 rows. I thought maybe pre-swapping would help. suppose for each iteration we could print how this is changing. The goal is to get a echelon form, and then, oh, I guess once we get to echelon form, wait, I thought we filled those zeros all the way up. Okay, yeah, zeros 2 up, 0, 1 up. We don't go all the way up. We only add it to all the rows below, right? And I think I made a mistake there in the algorithm. So each column, we add that rows column to all the rows below, to all the rows that are below. Oh, I'm doing that. N plus 1 until matrix length. Okay, and then when it's in triangular form, at that point I could solve it by hand. Oh, and I guess we wouldn't return the head. We wouldn't return the head just yet. So this assert is always going to fail. So we're going to check echelon form, assert echelon form, matrix.tail. You know, we could do this matrix.zip with index.tail. And the first, we don't even need to do tail. So row, and there's an N or an M. And basically we check that for N, for N from 0 until M, assert equals 0. Yeah. Okay. And after we get to echelon form, we do this thing, basically apply one up to the other. Maybe we just print that and solve by hand. We add some multiple of z back up to, or some multiple of the last row. What we've done here is add the last row to everything. So L2 plus 1/2 of L3. Yeah. And what was the thingy called? Pivoting. Hmm. I guess this row here is called our pivot. Let's call it our pivot. And why are we doing a for loop here? I can't remember. So we have our columns for each of our columns. Oh, we should just yeah, like for the first column, we choose the first row as our pivot, and then for the rows afterwards, so that's where the M comes in. N plus 1 until matrix dot length. N plus 1 until matrix dot length, just all the possible rows. Row 2 is the row that's going to be eliminated. What exactly is pivoting? Is it just swapping rows? And then I don't know why this doesn't show up first as problematic, because isn't that diagonal, diagonal, diagonal? Wait, right now there are no zeros in any diagonals. Pivot N. Our pivot in that column should not be 0. It could be the case that this was somehow zeroed out accidentally using one of these other. I guess that would be less likely if we moved like these up here. Okay, we still have this one here, which would be problematic. Then we need this one here not to be a 0. I guess we could take the first one and put it there. Oh, this is going to be a case. Oh, wait, we need to actually do it like that for each. Oh, 4, 3. Oh, hold on. Wait. 4, 3. Pivot N equals 0. We were looking at 4, 3. It doesn't matter which one of those we're looking at. N was our pivot. So 3. 0, 1, 2, 3. This was our pivot. And this value, 0, 1, 2, over here was 0. Like, did we go too far up in zeroing stuff? No, in the last term we would have done this. I'm just gonna print where all of our zeros are as per each iteration. I guess after each iteration of the year. Yeah. Or how do we do these? We could do this with indices. We could just do this with values. Okay, so for row in matrix, do for value in row, do we're gonna do a print. We're gonna do a space. I'm just gonna like put in a one if it's not. So if b is equal to 0, then 0 base else 1. And then we print line. Okay, now we can see it at every step. And actually, we have a lot of shit to comment out because we don't want this causing. I guess we're gonna go to the bottom of the sheet anyway. We don't need colons for 2. There we go. I guess at the end of all of this, let's just do another print line. Or yes, there's a space. Wait, I put that print line in the wrong spot. Yeah, we print the full matrix. And then we've changed a row. So we print the full matrix, and then we print a full line after printing the full matrix. Okay. Wait, so after the first iteration, things seems to have changed. One, 2, 3, 4, 5, 6, 7. Um, Nothing is changing, even though we set we set values here. Print line, matrix MK, before and after. Before and afters. Okay, like before and afters are happening. And they are typically different. So that's cool. Well, hold on. There are a lot of cases where they're the same. But those are probably fine. That's probably where it's already a 0. I'm just going to add a skip step here. Um, what did I have if matrix M n is not equal to 0? Um, yeah. Okay, and if we were to do this, then a lot of those redundant ones will disappear. that always results in a change. If we actually get new worksheet output. You know what? This output is too big. Let's comment stuff out. So everything from we start doing this time stuff to here when we start doing the math stuff. Basically, this check was supposed to check basically that row 2 matrix M and is not 0 because it's going to do nothing. But that doesn't seem to have changed anything. Go back to looking at just the matrices. Copy the worksheet output, copy to clipboard. We go through 3 iterations. And the value apparently doesn't ever change there. I mean, some things. So some things change. Well, after the first iteration, nothing changed. And also, those aren't the values I would have expected. If this is done like before any of that. So let's switch back to that again. This is our matrix printing line. I'm just gonna print the whole thing before we do anything. Oh, we have to wait for it to run. Make sure that runs. Wait, has it run? Validating. 1 second, 2 seconds. There we go. Why are there still so many rows? Like, where's all this coming from? Must be like way above. Anyway, we ended up with a longer thing. So this is how it looks when it starts. Yeah, that's good. And after 1, you don't end up with zeros in the bottom row. This factor might not be quite right. I mean, it should be. So we're taking like the reciprocal thing we're leading, right? Divided by pivot n. A for n until pivot length. We should do it from 0 until pivot length. Yeah. Oh, we should do it for the entire row, which would be pivot dot length. 0 until pivot dot length. There we go. Okay, now let's take a look at this. Ugh, that doesn't seem right. Did I actually copy it? And I hate that I have 135,000 lines. I think that's slowing down my editor. Let's look at what else is printing. Any huge outputs? Val hailstones. If I turn that into def, oh, these two print lines, those are problematic. Oh, remember when I was looking at angles? Okay, in path. Sure. Intersect, whatever. Intersect 3, that's not gonna happen. If there are other print lines happening in there, yeah, this print line we don't want to happen. These print lines we don't want to happen. Okay. Now we can switch to Scratch. And oh, much fewer rows. That's so much better. But we're still not getting more zeros in the bottom. In fact, after the first iteration, we lose some zeros in the bottom. And you know, there's some rows I would have expected. Well, after the second iteration, you'd think some of these rows here would no longer be zero, right? Okay, if you take a closer look at this algorithm, it's just a bug in here. Switching these values should work, but we just have a bug in the algorithm. Um, I'm going to define a print matrix method. Def show matrix zeros. Yeah, I'll just call it show zeros matrix. This thing exactly, and then we'll just have a show zeros here matrix, and after each iteration we show zeros. Easier to read. And then when we're done, we assert the echelon form. Right now, this isn't even our problem. Okay. So we are iterating over the columns. I guess this could like be an iteration over rows as well because we're choosing pivot rows, right? And the bottom row will never be a pivot. Whatever. We'll just keep doing drop right too. The last row will be a pivot though. And then m from n+1. So all the rows that come after the pivot until matrix out length, sure. And then this check just to remove redundant stuff. And then the factor is going to be row 2 and divide by the pivot n. Uh, is it, let's say the pivot has like a value 3x and row 2 has value like 2x. Then what we want to multiply by, or we want first row multiplied by 2 over 3, which is going to be row 2 over pivot n. Yes, this is the coefficient in the pivot you want in the denominator. So the factor is correct. What's the condition on 3, 3, 4? Oh, this just removes redundancies, right? So if that row is already at 0 at that place, right? In this case, the factor would just be 0 anyway. If we're not going to do anything, then just continue. So that shouldn't change anything. I can comment it out for now. But the factor looks correct to me. And for k from 0 until pivot dot length, but for every element of k, essentially, or every element of the row, of either row, this could be row 2 dot length, do matrix mk. Let me double check this. Mk, right? This is basically row 2. Matrix M. I guess I don't need to give that the name row 2. In fact, this might be easier to read if I just inline that completely. The factor equals matrix M n divided by, yeah. Divided by the pivot at n. um, yes, I should do that. You're right. Good idea. Good test. Okay, example. And this is an array of long. Oh, and I'm making assumptions about the number of rows here, I suppose. There should be, as long as there are more rows and columns, and this can be matrix indices dot init. No, that will be long to sit. If there were conversions from long to integer happening, you'd see yellow squiggly lines somewhere. Oh, this here can be of arrays. Okay, so let's look at the Wikipedia example. Oh, hold on. I'm doing division with longs. I'm dumb. I'm dumb. I'm not gonna make an example. I'm just gonna turn this to doubles. Jeez. I guess I got worried about like 0.0 cases or something. Right. One right here. And I suppose I replace space 0 with 0 0.0. Okay. Okay, let's try this. Okay, we do get an error, but the assertion failed. Ah, great. Oh my god, that's what I was debugging? Fuck. I forgot I converted them from doubles to longs. Good catch, good catch. Ah, alright. It is too late. Too late at night. Okay, now we see this happening. Um, we see a bunch of zeros. Wait, why doesn't this have zeros? After the first iteration, this whole first column underneath that should be 0. And 4, and 3, and then, okay, something else is breaking. Because the bottom row is not zeros anymore. What I could do, I wonder if like some of those ones are actually just really close to 0. Um, how do I check that? So if the, I guess I could check if it's within 1 of 0. If -1 is less than v and v is less than 1, then we print 0. Else print space or 1 space. Okay, yeah, that's a good way to do it. Just absolute value. Um, okay, now we're seeing it. Okay, so the first column, but what happens here? I guess I need a bigger epsilon. Or maybe the last row is just fucking up. Um, if v dot abs is less than 10, right, we're never going to have, these values are way too large. Actually, some of them, no. I guess less than 1.0 is fine. I hit a 0 on my diagonal. Did I? I didn't though. I get if I hit a 0 on my diagonal, then I would get a oh wait, like a 0 here. Right, I get to divide by 0. Okay, let me check that. If pivot and the abs is less than 1.0, then we'll just throw an assertion. Assert false. Okay. Yeah, okay, you're right. You're right. I'm having a small value here that looks like it could be 0-ish. Um, yeah. Okay, time for pivoting. So what exactly is pivoting? Is it like swapping row values kind of on the fly? Like swapping two rows? And then I guess if I swap two rows, like if I swap this row with this row, I would then have to make sure that the leading zero there, well, actually, how would I make sure that the leading zero is gone? Um, so they're not on my diagonal. What if I just like switch around some values so that that maybe doesn't happen, you know? At zero. Uh, okay. Make that row n at the start of every loop. Okay. Right, largest magnitude. So before I do any of this stuff, okay, we can do that. So, hmm, we'll make that function. So def, I don't want to use the name pivot. Um, pivot matrix, and I guess we need like an n for the the column that we're using. That's gonna be an int, and we have a matrix. And you know what? Because I don't know how mutation works, like this can return a unit, right? Let me just do like a def foo. A is an array of int, and this will do like a0 equals 1. And then if we had if we did val a equals array 0, 0, 0 foo a, oh whatever, a, and now we print line a dot make string, sure, 1, 0, 0. Okay, just checking. I'm gonna call this like a reorder matrix, and n being our pivot. Okay, so we want the highest one there. We want matrix, the index where, and we'll swap that for whatever row is supposed to be the pivot. Yeah, and then we don't have to worry about the zeros that are below or whatever. Well, hold on. Okay, if I do that, let's say we've done this, and we're going to step 3. We can't just take any row, right? We don't want to take one of these bottom rows, because then the zeros will move away. Copilot does all right, doesn't it? Okay, so index where, although it also gets drunk sometimes. You don't want to take a top row? Find a low with largest magnitude leading number. Yeah, leading number for that. So let's say we've done 2 iterations, and now we're gonna handle this bottom right corner. Oh, I guess of these. Oh yeah, we can swap anything around. We don't want anything that's above. So of these remaining, we choose one to be a pivot. Okay, So let's do matrix dot drop. So let's say 0, 1, 2, drop n. I'm gonna zip with index. Sure, we're gonna have to add n back in. Um, actually, you want to find the index. So let's do matrix dot zip index dot drop n, and then we're gonna get the magnitude that's largest. So map. So we have row and m. Oh, this is gonna be an n. I'm just gonna say I. So we have a row in I. We want the first element. We want the nth element of that row. So row n, and we still want to keep the I because we want max by that max by. Oh, exactly. Crazy how it types what I'm saying sometimes. Max by whatever, and then we get dot underscore 2, and then we swap those rows. And this is the new pivot index. And then I guess we have the old pivot values. Pivot I. And we're just gonna swap those two. And I'll save the old pivot val, old pivot, close matrix n, and then or you have to edit the matrix. So or m I'll just do I until from 0 until we're gonna do 0 until like new length. That's not exactly what we want. So we already have temps. We should have done that. Let's keep that in there. So we'll do like the new pivot values is gonna be matrix. And new pivot I. And then just I. And then matrix new pivot I will get the old value. Matrix ni exactly. And then old ni equals temp. Cool. Oh boy. So now we reorder the matrix every time. Reorder matrix and matrix, and then pivot. That works. Okay. Assertion error failed with pivot 0. Suppose we could print the matrix before and after the reorder. We need to see values aren't just fake ones though. Let's look at the worksheet output here. See how things are improving. Okay, so first run through, there are no zeros along the diagonals. Okay, that column, that column, that column, that column. And then we have, wait, do we have no choice? At this point, we have no choice. How did this become all zeros? Did we accidentally like subtract this row from itself? Mm, yeah, I want to see more about what's happening when I print the matrix. So I think for any row, we can just print um, I don't want to print the whole value. I really need it truncated. I guess we could divide. Okay, we could take like 1/100th of it and subtract that from it, right? So print v minus v over 100. 100. And let's see what that prints. It's not going to align properly. Oh boy, no, that didn't do that didn't do it at all. If it really is row zeros and the algebra is wrong, yeah. Yeah, I mean, that sounds about right. We need more equations. I mean, maybe, right? Let's just take this again. How about this? When I find that, I'm just gonna print the whole row. If it's a full row of zeros, we're screwed. Wait, did I just write over my worksheet? Yeah, I just did. Okay, here we go. Copy worksheet output. Need to put this in Scratch. Nope, we were gonna print the whole. Oh, you know what? Assertion might be too aggressive. Right, there might actually be something that's just close. In fact, I'm gonna go back to making this just zeros. B equals 0.0. 1.0 might be too much. We might actually get 1.0. Okay, this assertion failed. Echelon. Not echelon form. Okay, but let's take a look at what happens. Oh, everything looks worse. Oh, right, because of this. I lower my threshold. If v.abs is less than 0.5. It ought to be less than 0.5, right? That might actually be a row full of zeros. So if that happens down here, we'll copy this. Maybe I should use big decimal. Did I use big decimal? Hmm. If it's less than 0.5, insert false. If it's 0, and then let's just show, I guess a pivot row. Wait, did that actually? The assertion failed, and oh, it's here. We want to make a string that pivots. I just want to print line it too. So we're going to print line. And we're going to use pivot dot make string commas. And maybe the same thing here. Oh, right, the assertion ran before we did the print line. 0, 1.4, negative E14, 0 0.0, 0 0.0, 0 0.0. There should be 0 0.0s. 2.7, negative 0 0.0625. 0 0.0625 doesn't seem too small. I wonder what the zero values are for the other. Let's make our epsilon 0 0.05. It can be like very small, right? Oh, and we're going to change the order of these two statements. Because that there at the very end just looked like a small value. Okay, the assertion failed, pivot 0. I meant to do like n as 0. Yeah, I'd like to know the column. When are we doing the print line? And good. And then we have this. And then we have this. That looks right. Are we just going too far? Matrix sign. So M is 5. Zero, 1, 2, 3, 4, 5. This one. And N is 4. Wait. 0, 1, 2, 3, 4, 5. we should never get to n. We should never get to m equals 5. Or we should never get to n equals 5. Okay, anyway, m by n, or mn, is 5, 4, 0, 1, 2, 3, 4, 5. That's the last row. We shouldn't be there as a pivot. 2, 3, 4. Wait. 0, 1, 2, 3, 4. That's weird. Am I mixing up m and n? Hmm. I should just import a library. I think Spire would have this. I have been over this logic here anyway. But why are we looking at the last row? M. M from n plus 1 divided by pivot n. Right, pivot n is one above that. Oh, so pivot n being 0, this is going to be nn. So it's going to be 5, 5. Yeah, it's saying 5, 5 is 0. And that should not be problematic because we shouldn't get there. So matrix indices, I think it just needs to drop right 2. Yeah, drop right 2. And then we get not echelon form, but I don't know that that's true. Because here we do have something that looks like echelon form. Oh, thank God the algebra is not wrong. Matrix NM dot absolute value is less than 0.0. Hmm? Hmm. A bigger. It says not echelon form, but it looks like echelon form to me. I'm gonna say that my assertion check is actually wrong. Let's print whatever m and n is. M, n. Or wait, n, m? I mixed this up, didn't I? It's m and then n. Yeah, okay. Yeah, the assertion is just wrong. Okay. Wait. At 1 and 0? Oh, right. Yeah, the assertion's wrong. M equals 1, 0. Wait, that's 0? Oh, wait. That's equal. less than 0.05. Okay, cool. Cool. Yeah, you caught it too, the equals and the assert. Um, we're so close, we're so close. Now we just go back up. We go back up and we can get all these values and we can assign them. User code, or wait, whatever. So we have our system of equations. We get into echelon form. And then now what we're going to do is how we reduce. And I'm going to get Copilot to help me here. So for M index, for M from the bottom to the top, matrix.indices.reverse, and we're not going to do it in the top row. So dot drop right 1. In this case, like this should be 0 until 5. In fact, we're going to hard code that because I don't want to like think 0 or 5 until 0. So by -1. Right, we have 6 rows in our matrix. Cool. Is this all just right? I'd like to vector that. Vector. You know what? Hold on. I'm just gonna let autocomplete from here. Okay, I don't have libraries, but I do have Copilot. And then return matrix.head and to vector, we get nans. Oh, m minus 1 is 0 by -1. Yeah, m minus 1. So let's say we have 5. For n from we don't need to do any transformation to the bot row, right? We just are. So that's a pivot. We're just going to do something to the row above it. So we don't even need to do for val row. Matrix n minus 1, right? And whatever the factor is going to depend on the value in that column. Val factor, we're going to change m, which is rather m. So row m minus 1 m divided by pivot m. That makes sense. Right, in this case, it was like, okay, in this case here, we're starting this way. We want L2. L2 is going to be, oh, we have to turn them all into 1s, right? So, oh, wait, the right column becomes what we're looking for. Yeah. So it's not matrix.head. matrix dot transpose dot last. And yes. Okay, so here's a factor, and then we change everything in that row. So for k from 0 until pivot dot length, sure, that will do. We'll just change everything in there. Matrix m minus 1k equals matrix mk times a factor. And again, the factor was the one above, divided by one below. So 1/2 divided by -1. Which is just -1/2. So what we're adding now is -1/2 of this one. Plus 1/2 of L3. How's that right? No, we're subtracting 1/2 of F. Oh yeah, we're adding 1/2 of L. Oh, because we minus equals. So there's a minus in here already. Right, the factors scale it down to the appropriate size. Okay. That looks good. And now we can get the values. That's still wrong. You got a bunch of numbers. Let's show the zeros of the matrix. Those zeros, matrix before that last one. So after row echelon form and after we reduce, oh, after we reduce, this happens. So matrix m minus 1k minus equals mk times factor. Factor being, again, m minus 1, in this case, like 1/2 over -1. 1/2 over -1. Okay, I'm going to test this on the actual, on this Wikipedia problem. Bye-bye. Wait, shouldn't we add that? We should add that. Is there a problem now? Also need to scale row m by 1. Matrix over back substitute. Yes. M by row m by 1 over matrix after you substitute. Matrix m. I'm not understanding that quite yet. Going to parse your comments, but I'll get there. does not appear to be showing anything. That's weird. Is there no worksheet output? Match error. Milestone. Match error when parsing. Wait, what? We're totally fine at parsing this. Since when was that an issue? Oh, did we change the example? We changed the example, didn't we? Whoops. Okay, we can fix that. So 24. There we go. Okay, now let's look at this. Go scratch, paste it in. We start from the bottom and we are working our way up. And K from 0 until pivot dot length, matrix M1K plus equals matrix MK times the factor. Yeah, the one above being turned let's just make this matrix MM. And in order to do this on the test, I need to actually use the right indices here. Matrix indices are reversed. These are the row indices. And we're not doing that all the way to 1 because we'll have like a -1 somewhere, or all the way to 0. Let's try Gaussian elimination. We are getting a bunch of nons. You need to end up with the actual ones on the diagonal, so you need a final scaling of row M. Oh. Oh, we need ones on the diagonal. Right, right. So we can't just remove all of that. Yes, yes. Okay, I see. So actually, like, remove the y here. Then we need to like divide that by 2. L1 minus L2 becomes L1. And then to get that 2, 3, 1, it's sort of like combining those two steps in one. And we just multiply. So we're gonna zip this. Let's zip. Mm, let's see. For M in matrix.indices, do. So we need to scale things back up. So this is gonna be like our 0 until 5. Factor is just on the left. So val factor equals I guess it's 1 over matrix MM. Yeah. X plus y equals 7, y equals 3, z equals -1. 2x plus y. 7, you subtract the y row. you can subtract 2 times the y row? No, L1 minus L2. Right. I don't know why this isn't still 2x. I guess they've done like, so this would be 2x equals 4. So whatever this is here, you divide. So we'll do matrix M, and then just last matrix dot length divide equals, so divide equals matrix MM. And we are getting a bunch of nons, and we are still getting our echelon form still looks wrong. Or no, we did get our echelon form, our reducing of rows. Maybe this is minus equals. Let's just guess and check. Show hover. That happens here. No, that's still not right. Hmm. So the factor, there's a 1/2, there's negative z here. We want to get the thing that we have to add. And what we add is 1/2 divided by negative z times this row. Or 1/2 divided by negative 1, which is negative 1/2 times this row. In this case, that becomes 3, 2. Yeah, we tried this on the example. Well, example, array. We have an array of so we have 2, 2.0, 1.0. Whoa, it knows the example. It knows Wikipedia. I've not written this before, right? It it knows I'm pulling an example from Wikipedia. How about that? That is wild. Okay, so let's run Gaussian elimination on the example. Not echelon form. BS, not echelon form. I'm gonna just turn off my checks for this one. Or you know what? Yeah, we show the matrix. I guess our show matrix for this can actually be the full matrix. Just definition of show. Yeah, we're just gonna print V right now. So what's the problem? At 0.02? Wait, 2.01. Where's our 2.01? So first we show zeros. Um, Start. And then midline after pivot n. Starts as 2.01. Oh, 2.0, 1 point. Okay. When we show zeros, we need a space. Print v and space there. Point zero, 1.0, 1.0. That's cool. Oops. Whoops. So after we pivot 0, we have 0 0.0, 0 0.0. That's cool. We don't go far enough. We need to go farther. I guess it's just a drop right 1 then. But didn't that break my first example? After pivot 0 and after pivot 1. Now it's in row echelon form. And then when does the next show? So this is after reducing. Oh, nope, we don't want to look at that one. Gaussian elimination on the example. So pivot 1, pivot 2, or pivot 0, pivot 1. Then after reduce, there is still a negative 1.0 there. Oh, we have to go all the way up. We have to go all the way up and remove 0 from everything. Okay. Okay, not just the one right above, of course. I guess so we have some variable m. We already have m. We have 4 m targets 0 until m. I don't even need to, we don't need to reverse it, just do it for all of them. So this m minus 1 becomes m target. We still have that division. And m minus 1 becomes m target. These do need to be indented. Okay. Now, we have 2.0, cool, the diagonals, and what we end up getting, vector, we should get 2.0, 3.0, negative 1. Hey, it works, it works. Fuck those assertions. We don't care about these assertions anymore. And in fact, comment this out too. So getting none here. It works on the example. And this is the after reducing. The after reducing didn't work quite so well. Probably some sort of divide by zero thing. Okay, let's look at this closer. Okay, start. Pivot 0, 1, 2, 3, 4. Pivot 5 is not a value. Cool. This is basically 0. Negative E14. After pivot 4, let's just look at this value. 0.0. This will say 0.0. This is 0.0. That's what my zeros look like. I never want to print it because it's like so long. Epsilon is like really small. There end up being a 0 there. Wait. Negative 1.5. E12. Right, that wasn't an E negative. I don't know whatever else I screwed up. Yeah, that's fine. E negative 13. That's 0 0.0. 0 0.0. A legitimately small value. But it's all zeros in the last row. That seems kind of scary. When you go from the bottom up, then 1, 2, 3, 4, 5. Okay, let's look at this again. Worksheet output, go to scratch. Those are all zeros in the last row. A row full of zeros seems bad. I mean, yeah, right? If you have 0z equals whatever, how can you possibly remove z from any of those others? You might not have enough equations. Oh. That in itself is already problematic. E negative 13, that's 0 0.0. Wait, we don't want that to be 0 either. That's too much. Let me start with and hold on, I want wrap. Toggle word wrap. Okay, there we go. Val matrix. If final value in all of these starts out the same. S picks 3. Uh, it simply can't be 0. And 1 doesn't end up 0. At pivot 3. My pivot 3 is already 0. Oh, after pivot 3 it's 0. This is probably 0, 0.0. Yeah. This has to be 0, 0.0. Hmm. I shouldn't really be doing this by hand. Like I can do this in my print tables function. Just replace it with a 0, 0.0. We could take like the first 3 and the last 3 to shorten some of these numbers. 1.00 E14, for example. Yeah, that we can do. But it still doesn't change the fact that we have, it's our algebra, right? It has to be our algebra if we're having, we've canceled out a row altogether. Mhm. Do here. I use different hailstones. HS1. Right? Says I don't know, 37. 128, 230. Plug in different values. Um, Maybe it doesn't error on that. It still errors. Okay, our show can change. 0.0005 and print 0.0 space. Else s equals v dot to string, and we'll do like s dot take take 4 plus s dot. So if s dot length is greater than 7, then that let's print it. I'll make it at least show up nicer. Actually, I'll put a scratch. Okay, values change somewhat, but oh, there's no output. Okay, we wait for that to run. It says it's run. It says it's run. I don't know what's that. Wait, is there? Oh, S is missing. Okay, val S. Okay, now we can copy the worksheet output. Oh, now there are a lot of nons here. And it happens sooner. 0.8 e negative 14. This should be converted into 0. Right, that's well less than whatever def show. We're getting a lot of nons that have do with our specific. Oh, we already end up with a lot of zeros, like right away. Gotta print a space. Let's print space. Making this messy. And we don't need these 2 lines anymore. That's making things harder to read. Now we copy the worksheet output. Oh, that's so much easier to read. So at the start, we have all these values. That's 1 pivot. We have all of these values. Bottom one's already very small values. Okay, maybe we just have like bad values for this. What's the last value in any of these? 2.7 E16. Uh, 73, 218, 134, 124. Okay, let's see if those values get us something nicer. We don't use these to be pivot dot length. I from 0 until matrix dot or matrix dot head dot indices. I from matrix dot head dot indices. There we go. Start seems reasonable. Pivot 0, we have that. Pivot 1, we have that. Pivot 2, we have that. And we're starting to get some things that look like zeros. And here, oh, look, we're getting identical values. We're getting identical values for some of these at some point. That tells me we just don't have enough data. Our algebra is bad. We didn't actually use all of the equations. Okay. Or we reused some of the same equations too many times. Oh, I know where it might be. So let's go back to day 24. Uh, okay, here we have two equations. Well, I mean, this is our one big equation, right? It's our first time having anything. Get other equations like this. And was simply changing to x3 here not enough? So what we did was change 2 to 3, and then we changed 1 to 3 using the same 2's. I think like the minuses might have different orders or whatever. What we did, yeah, you probably should end up with like zeros over on this side too with the x. And yeah, these all have it. Well, these all have VXR, sure, but these all have this Z delta. Okay. How would we change this to get rid of the Z deltas and what exactly is redundant? I think it might be fair to have like this and this. Let's start with that. 1, 2, and 1, 3. What if we get like, let's start over again. So that's probably fair. And then how did we end up with like, YR is missing? We should try replacing YR. We replace Y with Z. And then we should try replacing X with Z. We never tried replacing X with Z. Yeah. So replace Y with Z. Okay. And then we're going to do another copy of this, where we replace X with Z. So wait, the first time here, yeah, we just replace one, we just replace 2 with 3. Is that fair? Can I like also replace 1 with 2? Maybe I should do that. One with 2, 3, 4, 6, 7. Okay. Great. Now place Y, Z, 1, 2, 3. And then we replace x with z. Oh, yeah, we had redundant ones, right? Because we had 3, 2, 1, 2, 1, 3. We didn't need all those combinations of 3, 2, 1. Yeah. And we forgot to do any like equations that have z and x or z and y. So here we replace x with z. 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay, now we can reorder these. Okay. Attempt to getting equation. Take these. X, Y. Add zeros. 0.0 plus 0. Plus that. And take this back because we'll have equals. Cool. Plus 0.0. Whoops. Yeah, I guess we don't need to draw this out as much as we're doing. We can turn those commas and stuff into zeros anyway. Okay. Why is there a misalignment? Oh. What? I screwed something up in those last two rows. Okay, let's try again. This dr, bzr. Oh, they both ended up as z. Whoops. Yeah, okay, I did the wrong thing. Okay, so for z, just copy like this row. We have x and y. We have x and z. And I think we want z and y, so we take this row here. Now we replace x with z. I have a feeling I changed something I wasn't supposed to. Okay. X with z. Nope. Nope, we're changing stuff. Not supposed to. Should start here. Or no, we're changing y with z. I see. This is wrong again. Okay, we're gonna change X as Y here. We've already added Z. Yeah, place X with Y. One, change something we're not supposed to change. Y. Is it starting? Here, okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now that's good. Um, then we have Y and Z. We can just shift this over. Oops. And add space here. You're so close. And then we convert this. New code. Uh, line up. That should line up. Oh, it should be times. Just this has times in there. Okay. We're gonna remove those anyway. In fact, let's just get this and we're turning these into vectors. Um, that plus. Remove that plus. And 0, 0.0. Cool. Uh, 0, 0, 0.0. And another comma here. And if you space this out, this should line. Okay, this time using arrays. Convert it to get in there. And now our function, our call of that function, you don't have to map to array anymore. Oh my god, we have values. We have values. Okay, let's go look up to before we tab 2. So we have we have a vector xr, vxr, yr, byr, zr, dyr equals this. And val ants2 equals xr. What is it? Pull up admin code. Oh, where is it? Calendar 24. What do you get if you add up the x, y, and z coordinates at initial position? Okay. Let's actually look at these values. So xr, yr, yr, and then zr. And I guess we could add those up, sure. xr plus yr plus zr. And 2.2 long. Oh my god. Holy shit. I would not be doing this without you. Icy Black Deep, that was great. That was the greatest backseating I've ever had. And I very much appreciate it. But, I mean, fingers crossed here. Too low, okay. Those are like in the right range though, right? Those X, Y, Z values. Yeah. But it might be off by like something small. We can test this. So val rock equals hailstone position, whatever. And oh, we had test code earlier above. Let's see how close that is. Times. Yeah, let's get the times. Okay, so times for this guess of rock. Okay, 9.17, 9.17. This looks correct, right? Like all those values are the same. Um, I move this further down. Deviations, whatever. Okay, times rock. And the sum of those deviations, let's do that. Let's just do all of these. So let's do dev rock. These are subtracting from the average. Okay, so I guess it's like very close. What does this get us? A bunch of fractional average. Okay, some of the differences for each row. And they're tiny. Okay. Makes sense. Good to know the scale of the answer. Let's do dev2 and let's do standard dev. Dev2. Devs. Well, pivoting. I might have to. But like that. Okay, so standard deviation is 1.1 E11. Um, let me see. I want to see the test on the example again. Right, 2.0, 3.0, 1.0. Could just be the case we don't have enough precision in our double. I mean, surely Eric wouldn't be that mean to us. These are pretty big though. So this dev2 was a sum of all the deviations from the average for each of those columns. The rock, precision. Do you get precision values like this? Velocity, 19, 197. What if I just hard code that to 197? What was that? The Z velocity? Yeah, I'm gonna hard code those and see what I get. Oh wait, that doesn't change anything. I mean, it changes these results here. So it's supposed to be 314, 19, 197. 314, 19, 97, right? And do these things change at all? Oh yeah, we get a bunch of zeros now. That's good. That's good. But this here, what is this? The sum of all the deviations. Let's just look at times rock. 4.0523. Okay, so these times for each rock are very similar, but they're not exactly the same. Yeah. Yeah, I'm gonna take them back as integers. And maybe we're close enough that we can just play with them, right? So our answer, we're going to do this based on rock because we're going to keep testing rock until rock.precision.x, dot round. Round. What is round? It gives a long. No, what? We can take this two vector dot map dot round. I'm still gonna do this in terms of this rock.position.x plus rock.position.y plus rock.position.z. That is a different answer than I tried, right? No, that is still the same answer. Okay. But I want those values. So let's look at xr dot round yr dot round, and then cr dot round. And we're going to plug those back into our rock. That updates. Okay. Worksheet output. Let's match. Paste it. And these three values. Be this. sub XR 133. I wonder if Copilot can figure the rest out. Nope, Copilot's not even active in the Scratch worksheet, sure. Okay. Okay. Now let's play around with these a little bit more. So for example, like these times are slightly higher than these are all their times. I want to know like I guess when I take the average of those, it turns to 0. This dev 2. Yeah, it adds up their deviations from average. We want this to be all zeros. Let's see how this dev is defined. Okay, we get the average of those three. That should always be fine. We add the differences from the average. Yeah, we want that to go down to 0. Play with different values then. Actually, before I do any of that, just make a copy of this so we can edit a few times. And then we have a velocity. Yeah, 49. Well, that's 50. And maybe as a metric, I'll take the sum of this. Like this should end up being 0. Double not number. Oh, there are nods in there. Why would it be non? I don't see why it'd be non. We're just getting the differences of each from. Oh, I guess that they were all 0. Well, no. Well, the average of the times are all the same. Should just be um like xt basically, and then it's whatever minus itself. 0 plus 0 plus 0. I don't know why that would non. Okay, let's look for the value for which it nods then. Um, call this dev3. Uh, dev3. And we're going to turn xt, yt, zt to that sun. And we do dev3 for each print line. Dev3 for each print line. Once I have like a metric here that works, I can just do fiddling with the positions, like +1, +2, whatever. It could be something like this. For dx, dx from -10 to 10, dy from negative, exactly. Then yield, we yield a new hailstone. Basically, that plus the dx and dy and dz plus d x, y, and z. Right, that's trying 1,000 different ones, and we're gonna look for one of those that has the best value. About possible rocks. We probably don't need -10, but like we can loop through 1,000. We haven't choose somewhere. This is not a value. Okay, just need friends. Okay, dev3. Let's see the ones that end up in non-infinity. The first value, 3.7, 3.7. We get infinity. Is a time infinity? Okay, let's just look at the times then. Whoops. Times to a rock. Are some of these times going to be infinity? Yeah, some of these times are infinity, which means they're not even viable. Okay, so that could be a metric. Like, does it not contain any infinity? And we could look, I suppose we could look at this hailstone. If there is an infinity, give us that hailstone. We could compare that with a rock and be like, and see what's wrong with it. F time. I shouldn't have done this in terms of map. I should have just done like for a hailstone. Whatever. We would get infinity if we divided by 0. Rock guess.velocity.x minus xv. They have the same velocity. It shares velocity with the rock. Yeah, okay. So it looks like some of these share velocity with a rock. They 24.text 2023 y and z. Is there a 197? Like right here. There's a 197. Um, oh, one thing I could try is just changing the values of the hailstones again and see if we get a more accurate guess for another 3 arbitrary hailstones. But other others around that same speed, like this one's 343. We need to be like behind that one. In this case here, oh, let's make sure none of these are negative. Any of these times, times the rock, are any of them negative? It appears none of them are negative. Wait, is that our only infinity value? No, we have 2 infinity values. So there's an x value matching at some point. We can search that with @x. So at 314, at space 314. Okay, so it might be values of the velocity that are slightly off. Let's make them higher, 315 and 198. And now, do we still get a none? We don't get a none. Let's look at times. Um, those times look the same. Nope, not quite, not quite. And I mean, of course, that would imply that our decision was right, which it's patently not right. We've tested that, right? Like this doesn't change. Wait, 33041. I don't think I tried. Well, why is it 41 now? 29, 25, and 67. 29, 25, and 67. What changed? Is this after I did the round? Just try that. Wait, this is too low. Okay, this value is too low. Oh, wait, they were both too low. Okay, right. Um, and it could be the case that it's far enough too low that doesn't matter. Okay, let's look at other HS1. Let's make this 83, 144, and 238. Add one more. Yeah, maybe you can still brute search around what you got, but it still could be a pretty big search, I suppose. So wait, what do you mean add one more? Add one more, add more equations? Hmm. Did I get the same answer after that? Oh, right, rock is defined here. I'm just gonna set this back to the default values. And we're going to uncomment this. See how that changes. Now we get 42. 5, 7, 8, 1, 7, 42. Val HS at 93 and 248. 41. I'm still getting answers close to the same thing. Right, remember which 3 stones I use. 45. Just keep adding 1 and submitting. It doesn't show you that if it's okay, 142 is too low. At some point that has diminishing returns. Would it be 3? Maybe some answer in here gives us 3? Guess wait 1 minute. Okay, in a minute, I'm gonna try 43. I mean, this looks pretty close though, right? The times for the rock. Oh, look, this has no infinities. And this is the rock that came out of the Gaussian elimination. Whoops. Yeah, exactly. I mean, after mapping around. Oh, I guess I mapped around here and then never did it. I should map around here, not map. Maybe I don't need to do that. I'll just convert it back to double again anyway. Well, I do want to do that for the vectors. Yeah. Okay, did I submit 43? Wait, I can't remember if I've submitted 43. I don't believe I did. Oh my god. Uh, you're right. +1, +1. Okay, I need to claim my 25. Push the big red button. Boom. I'm done. Oh my god, I'm so tired. I see Black Deep. That was awesome. That was a lot of fun. I can't believe you stuck through with it. You really helped me there. Ah, jeez. All right. All right. 5:20 a.m. I get 4 hours of sleep and then I have to do stuff. Fuck. That's fun though, I'm not gonna lie. Yes, same here. I'm gonna try sleeping normal hours. And it's gonna be easy because I'm gonna be so sleep deprived, waking up early today, that I'm gonna want to go to bed at 8 p.m. tomorrow. So I'll be an early bird hours. Oh, I want to look at leaderboards. Are you on here? Hey, you're not in here. You should join so I can see how you're doing. And Scala Center leaderboard. I ended up on top here. So, whoop. Greater than 24 hours. That was a first for me. But I got it done. And as the 4th one I finished altogether. Yeah, it's a first for part 1. So I have that to hold on to. I beat Benji by a few seconds. And like all these 1 hour delta times, everyone had to finish 24. Wow. Oh no, no, no. No, they did all finish 24 beforehand. I should have just taken the whole day off today to finish. Oh well. Got it. Got it. I can sleep in peace. Thanks, Icy Black Deep. Let's do a quick raid. See who's still finishing. Um, Ash Cop is seriously doing this in. Yeah. Okay. Raid. Bad Cop. Okay. Oh, it's only. Small raids are fine. Yeah, everyone's gone to bed by now. We raid anyway. Well, thanks. Have a good night. It was good to code with the Icy Black Deep. Um, Midnight Simon.